All right. So thank you all for registering to this course, Machine Learning in Geosciences, Existing and Novel Tools to Mine Geologic Data. I am Bulbul Ahmed. I am a postdoctoral research associate at a computational art science group at Los Alamos National Lab. So today we would like to showcase few machine learning tools that we think are very useful to analyze geological data and make some prediction based on the analysis. And I'm one of the course leaders for today's workshop. And Monty, he's another course leader. Monty, can you introduce yourself?
Hi, everyone. Thank you very much for joining us. My name is Velimir Veselinov. I go by Monty. I'm senior scientist at Los Alamos National Lab. I have been involved with various type of earth science problems over the years. And,
I'm super excited about some Brook Linen bedding.
Some of my colleagues, we have been developing a series of tools for machine learning. We also work a lot on data analytics, model diagnostics, model simulations, but machine learning work that we're kind of going to present today is touching on all this work that we have done in the past. So again, thank you very much for joining us, and please, if you have any questions during the presentations, feel free to interrupt. Thank you.
Thank you, Monty. So yeah, today we will show, basically we'll go through installation of Julia if someone has not yet, and then install some packages. And from there, in the meantime, we'll also introduce ourselves and keep working on installing packages and Julia, because we'll work using Julia. And then we'll work on introduction of Julia, why we are using Julia and future of Julia. And then we'll jump onto the unsupervised machine learning first. On unsupervised machine learning, we'll talk about k-means clustering, PCA, and then non-negative matrix factorization. And there are another novel tools that Monty wrote that is only available in Julia platform, not any other platform. That's called non-negative matrix factorization with customized k-means clustering. And then we'll show some real data that we analyzed in Great Basin geothermal data. And we'll show how we used it and what's our outputs. And then we'll touch on supervised machine learning and talk about what's their limitations and advantages. So yeah, having said that, let's introduce ourselves, and also let's go through installing Julia in the meantime. So Monty, how wanna go? Do you wanna ask name by name, or?
Yeah, just go after the list as you see people on your, but yeah, so as Bobo was saying, I mean, some of you might have already installed Julia and all the packages that are needed, but so I think the goal is to, if some of you have not done this already, to do this while we're introducing people who are here. So Bobo, go ahead.
Yeah. Okay, let me pull out the list. Then I'll call out the name, because in the Zoom the name switches. So yeah, let's go by at first Casey or Casey. I think Yeah, I can
I'm
hear
sorry,
you.
actually, Bulbul, did you ask for my name? My name's Isaac.
No, no, no. I
Oh, no.
Casey All Brighton.
Okay, sorry.
I don't know. Maybe many people I'm not sure, Bubu, how to.
I think, yeah, probably she's not here today.
Maybe it'd be more challenging that we're thinking to
Okay.
do all the introductions. Maybe I don't know. What do you think?
Let's
Comments in the chat.
Bubu.
Yeah.
Hi, Bubu. Yeah, I think Casey is on the call, but I think they are not maybe on their computer right now. So we could call someone else. That's okay.
Okay. Yeah, yeah.
Oh, I could introduce myself. Yeah.
Yeah, yeah. Go ahead, Josh.
Oh, awesome. Awesome.
Please.
Yeah. Good day, everyone. Nice to meet you, but though virtually. I am John Akudike, a student at Texas Tech University, master's student, and I'm the student volunteer for this short course. Thank you so much.
Thank you, Josh. Then, okay, let's go by Nikita. Are you here? Oh, Nikita. Yeah. Forgive me if I mispronounce your name.
Yes, that's correct.
Yeah, can you introduce yourself?
Are you saying Nikita or Nikki? They're close.
Either is fine. Nikita, sorry, I was having some speaker issues. I just managed to get you all on my audio. My name is Nikita. I work for the U.S. Geological Survey. I didn't hear if there was any other prompt to what introduction you're looking for.
I think that's good.
Okay.
Okay, so now let's go by Nikki.
Hi, everyone. I also work for the United States Geological Survey. My duty station is in Eastern Washington State in Spokane, and I work within the Mineral Resources Program, and I'm interested in seeing, working with my colleague Josh, who incorporates machine learning into mineral resource assessments and just keeping up to date. It's clearly a cutting edge feature of a lot of different programs, so I'm interested in learning about it. Thanks.
So what kind of tools you use, like mostly supervised or non-supervised?
I'm going to let my colleague Josh answer that.
Okay, no
Calling
problem.
him out. Yeah.
Okay, so now let's go by Ali Ling.
Hello, I'm Ali Ling. I work for a consulting company called Bar Engineering out of Minneapolis, doing water treatment and water quality types of work. We've been kind of looking into using machine learning to look at both water quality and kind of monitoring going forward. And I'm just kind of trying to hear what other people are doing and what kind of tools they're using.
Okay, thank you. Then Larry.
Hello, I'm Larry Lai. I'm PhD student, 5th year, University of Oregon. I study nothing related to machine learning, and I just got interested in that. And I do some research and read some paper, and people use machine learning to do strategic analysis. So that's why I'm here. Thanks.
All right, thank you. Solomon.
Good morning. I'm at Colorado College. I'm a structural geologist who studies rock fracture mechanics usually. And I use a lot of numerical tools. I've not used machine learning, so I too am interested in how I could use machine learning in any of the analyses that I do.
Thank you.
Thanks.
James Hayes.
Hi, yes. Hello, everyone. James Heiss here, assistant professor at University of Massachusetts Lowell. research is in hydrogeology, specifically kind of coastal hydrogeology. So interested in applying some of these methods that we're learning today in research. Thanks.
Thank you. Adam?
Hi, Adam Ayano. I'm with the Pennsylvania Geological Survey and their Mineral Resources Division. I guess I'm a little bit new to machine learning, so to speak. So I'm curious what you have going today, and interested to see this in action.
Cole? Thank you, Adam.
Hi, it's Sue Ting here, and I am a PhD student at Texas A&M University, and I do experimental rock mechanics and earthquake rupture simulation. And I'm also interested in machine learning, especially the Julia programming language, because I found it recently that it is a very fast and handy, and probably in some cases more capable than Python. So looking forward to attending this class.
It is, thank you. So, Cole?
Yes.
I think he's saying Cole,
Oh.
C-O-L-E.
Yeah.
Oh,
yes.
oh, sorry.
No worries. But my name is Cole Heap, and obviously by my name, I'm a geologist by trade. I'm a PG with several of the states here in the United States, but I also work for an energy company in California, where I have dabbled in deep learning in a GIS. I'm also currently enrolled in my second master's degree program at USC in the spatial sciences. So I'm dealing with that. And my first master's program at Fresno State, Cal State Fresno, I actually dealt with the R programming language using supervised learning to predict the depositional environment involved with turbidites. So whether or not that be in deep fans, or if that be in channelized turbidites. So I'm familiar with deep learning and I'm familiar with machine learning, but I've yet to use Julia.
Okay. Yeah, you'll learn today. Dan Starmer.
Dan Sturmer. I'm an assistant professor at the University of Cincinnati, and mostly work in basin analysis, but my work kind of spans geochemistry and geophysics and sedimentology and structure. So I don't use machine learning, but I am interested to hear more about it and how I might be able to use it.
All right, no problem. So Drew Lakowski.
Hi, everyone. I'm a assistant professor at Montana State University. I specialize in structural geology and tectonics, and I'm interested in using these tools in my research.
Thank you. Erin Miller.
Hi, I'm Erin. I'm a PhD student at the University of Southern Mississippi, and I study the effects of sea level rise on coastal systems. And I'm just interested in learning more about machine learning.
All right, thank you, Erin. Hayden Yates.
Hi there. I am a master's student at Montana State University, and I don't know that much about machine learning, but I'm excited to attend this class and see how I can maybe implement it into my research. Thanks.
No, thank you. Isaac. I think you're muted.
Sorry. Hey, sorry. Hey, everyone. My name is Isaac. I'm a PhD student at Texas A&M University, like Sue Tsing. And I am a pure geologist in that sense, but I've recently been shifting towards image analysis and of microscopy images. And I've been dabbling in a bit of machine learning over there, mainly supervised. So I'm hoping that if I can pick something out of this course, it'll really help me with my research. Thank you.
You're welcome. Yipeng Zhang, if I'm saying right.
Hi, everybody. I'm Yipeng Zhang, a postdoc researcher at University of Texas at El Paso. I'm working on combining numerical models with machine learning to develop surrogate models so that people can come up with optimum pumping schemes to sustainably develop the coast aquifers along the east coast of Florida to prevent seawater intrusion. Thank you.
Thank you. Wen Rong Gao.
Hey, good morning. My name is Verun Cao. I'm assistant professor from the University of Nevada, Reno. I study tectonic and mathematic process in Clean Orcs. So I have no idea about machine learning, but I'm happy to learn. Thank you.
Yeah, thank you. Young Jiang Li. Okay, Stefan. Are you there, Stefan?
Yes, that must be me, Stéphane Séjourné. Hi, everybody. I'm an exploration geologist based in Montreal, Quebec. I know nothing about machine learning. I'm not using it, but I'm happy to learn. Everything I can learn today is good. Everything that goes way above my head, that's fine too.
All right. Yeah, I hope everything will go good. Yeah, so I think I missed someone. If you have not introduced yet, can you introduce yourself?
Sorry, can I introduce myself?
Yes.
Okay.
Please go ahead.
Hello, everyone. I'm Yunxiang Li from Nanjing, China. I didn't have the experience of this, but I'm interested. I see how it can help me with my research in deep time polluting environment and polluting climate change. Thanks.
Yeah.
And I'm Josh Coyne. I'm with the USGS out of Spokane with Nikki Windsor. And I've been diving into machine learning using neural networks, weights of evidence, and gradient boosting machines to predict mineral deposits.
All right.
You covered me already, but I was having some audio issues. And now that I've heard the prompt and the more full introduction, I thought I'd just go back, give a little bit more detail. My name is Nikita Avdievich. I'm a geologist with the USGS at the Landslide Hazard Center in Golden, Colorado. So we do a lot of susceptibility modeling that usually falls more into the purview of classic statistical modeling. So I'm more interested in kind of broadening the horizons there, seeing what I could use machine learning for.
Thank you. All right, I think probably we covered everyone. If not, please introduce yourselves. So now I'd like to go ahead and check if everyone has been able to install Julia. Does anyone have problem?
I was able to install it, but anything in your PDF after set path, I got an error for.
On what, Windows or Mac?
Windows. From that last slide there.
So Windows, I think you don't need right now in path. You can just because Windows, there should be a logo in the desktop or somewhere in the programming system. You can install on the logo and it will open up. Can you open the Julia or not? I think that's more appropriate question.
Yes.
Okay. And if you don't work behind firewall, then you don't need this page, page 7 or slide 7. And okay, then has everyone installed iJulia, that Jupyter node that opens Jupyter notebook?
And there's some issues with this, and they're in the chat. one of you had issues with doing this, but hopefully this was resolved. You just need to copy and paste these commands that you see here.
Okay, so far, has anyone issues on this? The installing Julia or iJulia?
Actually, Stefan speaking, I don't seem to be able to just even copy paste.
I wasn't able to either. I have to manually enter
Okay,
the
I'll
code, which is fine. It just takes a little bit longer.
Yeah, I'll do this. I'll put them in the chat as well.
Okay.
Just a second.
We have to show the Julia page, Jupyter page, that if I want to make sure whether I successfully install it. Because yeah, I have run through all the slides and I can open a browser and with Jupyter, but I'm not sure if that's correct.
I think that's correct.
Okay, thank you.
Yeah. Now you can navigate there and go what directory you want to go, and we updated the GitLab or GitHub repo, so you can download new repo and then you'll get most updated one.
Gotcha. Thank you.
Yeah, and I put the commands which are in the note in the presentation in the chat. So hopefully everyone, we can copy and paste those in the Julia repo.
I just wanted to ask a question. I mistakenly downloaded 1.6.3 Julia. Is that okay?
It's fine.
Yes, fine.
Yeah, everything works on 1.63. I tested it yesterday as well. Yeah, and after that, again, I'm not sure how people were succeeding, but I'll copy and paste the rest set of commands which are just shown here. And this is really to and all this will take some time. So it might be the best just to make sure that everybody is able to do this, and we will start talking in introducing kind of the ideas that we want to achieve in the workshop, mostly because as many of you are not that much familiar with the machine learning methods, but maybe we can just kind of give you a high overview what is the difference between different supervised and unsupervised machine learning methods and how we can use them. And that Bubu will go in great details, but in general, machine learning is done for classification and regression. And maybe most of you are familiar with what regression means and classification what means. So we'll be touching a little bit also on these issues. So I believe if everyone is currently working and successfully copy and pasting the commands that you have in the chat, and while you're waiting for these commands to be executed, we can start chatting about machine learning in general. Does it sound like a good plan? You can clap or put
It sounds like a good plan to me.
Good.
Okay. Good. Yeah. Yeah, and if you have any questions, please ask. Don't shy. Yeah, we'd be happy to answer your questions regarding installation or any machine learning questions.
Yeah, and the other thing, which again, I'm not sure people, I'll just say, Julia people try to do a lot to make sure that all the packages are talking to each other. And if some of you had experience in Python, you might know that in many cases you need to keep different environments, everything to work, because there is a conflict between different packages. At least in Julia, the goal is that most of the packages will be talking to each other and there will be no need to do special management of different versions. So at least I hope, I mean, this is also be very exciting if for all of you these commands work smoothly and they don't cause issues. But if there are any issues, let us know and we'll help you to address those. Bobo, do you want to start some of the overall machine learning discussion?
Yeah, I think we can in the meantime when everyone is working, installing these packages. So yeah, as Monty said, yeah, we have broadly classification and regression. Then we'll go to machine learning, supervised, unsupervised, or physics informed machine learning. And what are the best tools for our work, like in geosciences? So classification, what do you mean? Like, we try to understand categorical variables or broad value like, or integer value like, whether a class is 1, 2, whether a number is 1, 2, 3, 4, 5, 6, 7, 8, 9. Like anyone who does machine learning probably starts with supervised classification. What it means, you have an image, you have images, and you have to understand whether it's images of numbers like 1, 2, 3, 4, 5, and we have to train that. Train means give those images and their data, true data, to machine learning algorithm, and it tries to learn or memorize, and then feed some new data and try to predict the corresponding value, whether it's a number 1, 2, 3. So that is what is classification. We try to understand broad value. It's not like continuous number like 0.1, 0.2, 0.3, 0.5, or 0.1 to 0.35, not like this. On the regression is we try to understand continuous value. And I think in geosciences, that's our most, like we try to do that. Like we try to perform regression and find continuous variables or predict continuous variables. So in a broad sense, this is the main two differences between classification and regression. And then also there are some interpolation, extrapolation things comes along, because in the data, we don't have all kinds of data. We generate data, or we get data in a range. So what machine learning sometimes does, it learns the range, and whenever it doesn't get a value, suppose it gets a value within that range, then it interpolate, or it gets value outside of the range, and then it tries to extrapolate. So it also does inherently both interpolation and extrapolation. And then, so I'll go through like what is supervised and unsupervised machine learning. So in supervised machine learning, we have data and their corresponding outputs are true values. So if a data has that true like corresponding output level, then we call it supervised. And if a data set doesn't have the corresponding labels or outputs, then we call it unsupervised. And physics information learning is that one when we introduce physics in the machine learning algorithm. So it learns both from data and also make sure that physics laws or physics model also satisfied. So in that case, we call physics informed machine learning. So those are broad classification of machine learning. If you have any particular questions, please let me know. And Monty, do you want to add anything?
No, I'm trying in chat to help people.
So Nikki Winston is having issue with import iJulia.
I was just given a solution by Monty of via DM and it worked perfectly. And so if anybody else wants it, Monty, maybe you could share it with the group. But yeah, that got me unstuck. Thanks so much.
All right, sounds good then.
Yeah, I'll send this to everyone again. When you start the Julia REPL, the first thing you need to do is these 3 commands to set environment of Python to nothing and import package and package at iJulia. And this should be working fine. And after that, if this is working fine, you need to do the second step, which is similar, but this will install.
Yeah, so Julia can also install Python packages and run on Julia platform. But sometimes it creates issue if there is some version issue or there is conflict between Julia packages and Python packages. So that's why we try to use no Python, like we try not to use Python. That's why we put the command as blank command. It means Julia will not look for Python anymore.
Yeah. I think, I mean, Bobo, if everybody is on track, you can start with your first notebook.
Okay, so in that case, I can start with my that was Julia introduction, and then I'll go for
yeah, maybe you show the screen and show how.
Yeah, I'll do that.
Or can start it, and when you start the notebooks, you can use. I mean, there are different ways. Depends on people how you want to open. There is. I mean, the easiest to use your browser, but there are other alternatives as well.
Okay, let's go from there then. Okay, so I'm trying to share a screen. So, okay, desktop. Awesome. Now, so this is my terminal window on Mac. So what I do now, so I already imported iJulia, and then I'm running the command ijulia.notebook, then close bracket, and then you'll see some command here, and then it will take you to the browser, And on that browser, I go to my directory where all my tutorials are, and I'm going to the notebooks and then Julia introduction. And here I would like to open Julia introduction. So I'm clicking on there, and it opens up. So that's how we open up Julia notebooks. Okay, so Monty, do you want to go ahead and start?
Able to do this? I hope we are.
Okay, so then let's go. So this is the only notebook that I'll go about Julia, because our main goal is machine learning and it's platform on Julia. So I'll give you just this introduction, but we have a lot of important notebooks here, like 4 or 5. You can go through them alone, and you can learn a lot about the syntax and what we can do, what we cannot do. So Julia is a kind of new programming language. It started in 2010. Primarily, it was focused on high performance scientific computing, like statistical computing and machine learning and artificial intelligence. So that was the main focus, and main focus was to bypass the traditional languages like C++, C, or Fortran, and make a modern language that is capable of doing what C++, C, or Fortran does. And that was the main purpose. And it is free open source compiler, and we have a lot of standard libraries, and also we have numerous open source packages, or we interchangeably use packages and modules. And you can find a lot of them using this julialang.org and or juliapackages.com. You can find what kind of packages are available. So till now we have I think whatever you need in statistics or machine learning or artificial intelligence, Julia has that, and on top of that, Julia is rich in physics information learning that no other language has the capability. And Julia is one of the very few languages that goes to the petaflop club. Monty, can you explain what is petaflop club?
Petaflop club is languages that were able to perform petaflop computations. And maybe you know that there is kind of universal challenging problems to perform petaflop computations. You need to do this on supercomputers. These particular petaflop computations were done on one of DOE supercomputers, and it was done, I believe, 2 years ago. I think there is a link related to this.
Okay, so yeah, thank you, Monty. And then it is ranked 5th most loved language. That's really cool, even more loved than Python. Most importantly, Python is really like good to understand language. And Julia is also like that. It feels a lot like MATLAB and Python, but only it's much faster, and yeah, it is way faster. And it is dynamic, expressive, and extensible. So now Julia, the computing has raised over $24 million to enrich its library and packages and take it to the next level. So if you would like to come to the Julia environment now, you'll not regret. So
hi, Bubu.
Yeah.
Yeah, I think there's a question on the chat box.
Oh, I'm sorry.
Okay. So yeah, so I canceled it. I import iJulia like this, and then I run this command iJulia.notebook and hit the enter, and
But
so
the issue is that you should have this thing what downloaded from SmartTensors tutorials. So depending where you put this will be in different locations for everyone, where SmartTensor tutorials is okay.
yeah, probably it's in download or wherever you put, you should go there. So
I'll put the link in the chat. Just people how to access these materials. You can just go to the website, and I'll just put a link what to do. So this is the link to the website, and here you can click on download zip, and I'll copy the link in the chat as well. And you can get this zip file and put it whenever you want, unzip it, and you have all the materials. And by the way, I'm seeing a lot of typos in the slides, and I'm fixing it in the real time when we're talking. So if you find laughable typos, don't laugh. I apologize for these typos, but we're fixing them.
so went wrong. Have you figured it out? Oh, okay. So yeah. So as I was saying, yeah, and so Julia is in a good track now for further development. So now the question is, do we need another programming language or not? So the answer is yes, because Python is mostly two language problem. Like under the hood, it runs a lot of C and C++. So for code simplicity, Python is his language, but in the under the hood, it uses C, C++, or Rust, because those are very fast languages. So, and sometimes that mixes up thing. But Julia's purpose is solve that two language problem. Is only thing is it writes everything on Julia and performs in Julia. And now the question is Julia really fast? Because it's written in Julia's own environment, not in Fortran or C++. And it looks like it is fast. If you see this figure, as compared to like C, Julia, Lua, Rust, Go, Fortran, and Julia is onto their range. So it is fast, and we solved many benchmark problems. Like we solved 1, 2, 3, 4, 5, about 9 benchmark problems, and on all of them, it performs really good. And we have also provided the link for Julia tutorials and support. And if you have any questions, you can put on Julia discourse community, and it's pretty active community. And now Julia is also have a Stack Overflow. If you have any questions, you can put there too. So I think you'll get pretty good response. And so So Julia has Julia replica, read, evaluation, print, loop. So on this loop, you can write your script, execute scripts, and then evaluate them, even if you need help. Like, so suppose in this Julia help, if you put the question mark and print and write the function you are looking into, or you want to know more about that function, if you write then, and you'll find everything about that function. And if the same name has multiple functions, it will tell that, okay, this function does that, blah blah blah. So you get instant on this replica. You just press question mark and write down the function you are looking for, then it will give you answer. So yeah, it is also comparison with like how many, I was talking about the two language problems like TensorFlow, PyTorch, GSA, KNet, Flux, like those Flux is written in Julia, is 100% Julia, but on the other language like TensorFlow, PyTorch, they're mixed up, like they're getting contribution from C++, Python, HTML, Jupyter Notebook, then Go, then Java and other also. But purpose of Julia is 100% in Julia. So if anyone wants to work from scratch, it will must benefit. He will be must like he will get a lot of benefit using Julia. So that's all about Julia introduction. If you have any question, please let me know, because now I'll jump onto the clustering, the machine learning, one of the first mostly used unsupervised machine learning tools, clustering, K-means clustering.
And at this stage, we hope that all of you were able to get your Julia notebooks working, because it'd be very nice to be able to do all this work interactively and be able to see the results in real time.
Okay, so should I move forward and open up the so Ali, you have access to all the notebooks here, and you should have access, and you will have access. So now we'll open the unsupervised _ML, and there I'm opening clustering. So okay, so Isaac is saying almost at the end of the downloading the packages, taking some time. Okay. Monty, should we wait for a little bit to give them more time?
Maybe just, I don't know. I mean, I want to make sure that everybody is kind of on the same page. So if all of you are able to open this clustering blind source separation notebook, try to run the first cell there, which is import NMFK and the other packages here. So hopefully, and this also will take some time. So start the first cell, and Bubu, show them in your screen as well.
Yeah, so here I'm on this line 2, like this Windows. So I'm hitting Shift and Enter on Windows, and Mac Shift and Return. So then it will run. Or you can manually run on this. You see the run button on the top. So on that, go to that cell and run it manually. Either way, it works fine. So it's running. Whenever you see the star, sign in the cell in the left, it means it has not finished, it's running. And whenever you see any number, it means it has finished its job, and we can move down. Yeah, so okay, what kind of errors you get, Larry?
I copy and paste the arrow message below, something like that. Is that a directory thing?
Oh no, okay, so I think you have.
Oh.
Did we say that we have to do install that? Let's see. Oh no. So
I hope. I mean, this is weird. I mean, this is error in a package which is not ours. And I have not seen this error, which is interesting, but try to do just import GeoD2 in your repo.
Okay. In Julia.
Yeah, I just put in the repo.
So doesn't he need to install it first?
I mean, it's complaining the GeoD is missing something, which I mean, for me, could be not important as long as.
I think imported. Yeah, imported to work fine. Yeah.
If import GeoD works, okay, you should be fine. Hopefully, import GeoD. And I'm sorry, this automatically capitalizes the first letter. Import has to be with small case. So as long as import GeoD works, you should be fine. If it doesn't work, I need to find how to resolve this problem.
Yeah, for me it works fine. Yeah, go ahead.
Yeah, hi. I installed all the packages, but now I just wanted to know how to open it. I'm able to open Jupyter, but it's not showing me this notebook. I want to know how to open this particular notebook.
So where did you put your the SmartTensor, like our GitHub repo?
I haven't taken it yet actually, so I just need to clone it into.
Yeah.
You clone and go there, and you'll find the notebook.
So I tried to import JLD2, and it just say arrow syntax. I would just copy the message from the Julia here.
Can you copy and paste in the chat?
Yeah, I'm doing. Hold on.
So I need to clone it into Julia repo, right? Or just.
This is from Julia repo. Should I need to install that package first, or?
No. I'm sorry. Again, when you do import, use small. Don't use import with first letter capitalized. And the problem is the chat automatically capitalize the first letter. So do import GeoD2 without capitalization of the first letter.
Okay, I'll try again.
I mean, this is just.
Yeah.
Same thing. Hold on. So the error message changed. Yeah, not found in path.
I think now you have to add it.
So try to do again import package at GeoD. I mean the thing that it's in. I'll put it again. So try to do this and see what we get.
Gotcha. Hold on. Okay, it's installing and import again, maybe.
Yeah.
Or
Install it and import it.
I mean, if this persists, I'll give you another alternative things to do. But first, tell me what you're getting right now.
All right, I finished installations and I can successfully import JLD2.
Okay.
Okay, I'll try to run the Jupyter again.
All right. Yeah, let's see.
Thank you.
I'm sorry. I mean,
something happened.
I mean, that's why we have this session. So
So Nikki Windsor, yeah, so she is successful on it.
Just to clarify again, so I downloaded the zip of the SmartTensors tutorial, and then after that, how do I get to this?
So did you unzip it?
No, about to. It's about to get unzipped in a second.
Okay.
So after unzipping, what do I do?
So then go to that directory using the browser.
Okay.
So do you see this
Yes.
browser?
Yeah.
So you see the documents?
Yeah.
So I have everything on my documents. Now I don't know where you put. So if you see the folder sign in the left.
Right.
So if you click there, then you have applications, data, desktop, documents, downloads. So where you put the SmartTensors.
Oh, okay. So I just have to go where I put the SmartTensors and then just open it from there.
Yes, yes, you got it. So like this.
Right, right. Got it. Okay, I'll let you know if there's any issues. Thanks.
Yeah, please let me know.
Can I get a follow up? I got sent error message in Jupyter. Just copy paste again, but I already import JLD2 already. So that's the message I got when I run the first one. So yeah.
Yeah, this is again. I mean, kill the. If it worked in your REPL, in the Julia REPL, maybe kill your Jupyter and start it again.
Yeah.
Okay, I'll try again.
Yeah, that will work. The Jupyter and the Julia replica, because they're working the different times in terms of environment. Sometimes they don't integrate. That's why you have to start over again.
So once I start over, should I import what is that package, JLD2 again, or just run the Jupyter?
Just run the Jupyter. I think it should work.
Okay, I'll try. Thank you.
So okay,
there is a question, Bubu.
Yeah,
Can you
yeah.
show how when it works fine?
So this is
when it works
what you might get.
Yeah.
So
you should not get error message here.
So when wrong, yeah, did you kill the Jupyter notebook and start over again? Okay, and then you also got it the same. Okay. And did it import JLD2?
Well, unfortunately, same message. Yeah, I start over the Julia. And
Yeah, I mean,
get that.
in this case, I mean, the other, I mean, can you, okay, I'm curious about something. So I'll ask you to do something else and tell me what is the output.
Okay.
Can you do this and tell me what is the output? I'm putting this in the chat.
Run this in the Julia REPL.
Yes.
Okay. Hold on. Restarting Julia.
Oh, import package you need first. I'm sorry. just do import package, and after that, this import package needs to be invoked. I was assuming that you already have it. That's why. Oops. Import package, not pack yet. I'm sorry.
Okay. I will pass the result. Is what I got.
Yeah, and this is the right version.
Yeah, that's weird.
So no. So now next thing you do this.
Okay, Monty, will you let him share the screen and see what he's doing that way? I think.
No, I don't need to share the screen. I mean, I can. You can also let him, but I don't need the screen. Try do this now.
Okay.
And I'm guessing that might something happened during the building of this package, because it's, I mean, it is definitely very weird. I never saw this error, but so many of you are getting it. So, by the way, are you on Windows, Linux?
No, Mac.
Mac. This is
Yeah,
even
probably
more.
that's the Mac problem. Yeah.
No, I'm using Mac all the time, unfortunately, even though I don't like it. But
okay,
yeah.
I finished the running of the package build things. Yeah.
So if package build is done, try to import GOD2, and hopefully this will work now.
All right. So now I start the Jupyters and try.
Or just try it first in the Jupyter in the repo. Just import GOD2 in the repo.
Oh, okay.
Import is like a load, or I mean, telling the code to use this package. This is what import is doing.
All right, done this import JLD2.
Yes.
Okay, so it imported.
So if this important doesn't cause errors, this should be fine. So if other people have these issues, everybody do this package build command. I'll post it again. Hopefully this will resolve the issues for everyone. I apologize. I mean, this is very strange. I have not seen this before. But other people, if successful, please go and start executing the cells in the Jupyter notebook that they're currently working on. So you don't, you don't need to.
Yeah, wait for us.
Same. Feel so bad. All right, just again, send message in the Jupyter.
But it worked in your repo. Okay, can you do these commands in the repo? Because I'm just curious. I mean, if you paste,
I mean, copy this in the repo.
Yeah, I mean, these commands, which are practically the first cell in the Jupyter notebook.
Okay, I'll try to run it.
I mean, you don't need to use the Jupyter notebook. It's preferred because you see all these things inside. But and as Bubu explained, I mean, your Jupyter notebook creates new instantiation of Julia notebook and of Julia, and when you do it in repo is another one, and they're two separate things, which shouldn't be different, but because of something they're different, and I don't understand why.
For what it's worth, I've not tried the rest of the packages, but when I tried importing an MFK just in the REPL, and that worked without any errors, but I do get the error in Jupyter as well.
So you get the error in Jupyter and you don't get the error in the REPL, correct?
Correct. Correct.
And when you open the Jupyter on the top, what version of Julia you see to be activated? Is it 1.62 or 1.63? Is the same version that you have it?
1.63.
Okay.
On both. Okay.
Yeah, I'm puzzled.
Okay, so
in this case, I mean, if you
no.
I mean, the
Monty,
only thing which I can suggest is to kill not only your Jupyter notebook, but also to kill your browser and try again to activate the Jupyter notebooks, because something is strange.
Yeah, also create new Julia REPL. That way it will integrate with the most recent installation that you did.
I want to second that. It seems like the browser or Jupyter's issues. I can run all the codes and got exactly the same result in Julia REPL, but I cannot do that in Jupyter. But I will try launch Jupyter again.
I think might be the browser issue. Yeah, you're right.
Any preferred browser?
Yeah, which browser is everybody using? Just curiosity.
I mean, actually, it shouldn't matter. I mean, this definitely, but who knows? A bit, but yeah, it's definitely strange.
I'm using Safari, but I do have Chrome, so
I use
we can
Chrome.
try both.
Yeah.
Yeah, Safari recently updated, so well, I will try again. Hold on.
Yeah, I'm using Firefox. Yeah, so Wendong said same browser issue, but good results in repo.
So is there a command that I can force it to open the Jupyter in different browser? Yeah.
No, it depends like what is your default browser. So it will go to your default browser.
All right.
So,
I just killed Safari and try again, but still not working. I'll try Chrome right now.
does Jupyter work with Safari?
Well, Jupyter, at least Python Jupyter notebook working well in Safari in my case. So.
No, it works. What I found in the Google. Okay, in that case, probably.
Same error for me in Chrome.
Okay. In that case, whoever like the browser is not working, then what I suggest, work on Julia repo and install this package.
Install that package. Okay.
Yeah, and that way you can see the all the figures on the terminal. Yeah, add it, and then we can work, just copy and paste this code onto the Julia repo, and it will work fine.
All right, finish import terminal extensions.
Oh, okay. So Monty is saying terminal extensions works only on Mac. You know, does 6L works on every?
6 works on everything.
Okay, on Mac, whoever has Mac, please use terminal extensions. Who doesn't have Mac, then use please 6L.
And this is only to be able to see, I mean, you still be able to see the results. So it's not critical to install these because otherwise the results will pop up in a separate screens. In one case, the results will be embedded directly in your REPL. In the other case, they'll be just popping up as external windows. So this is not of critical importance. I mean, it's your choice.
Yeah.
I mean, they're convenient tools.
And on the other hand, there's another solution. If you don't want to work on this notebook at all, you can just see the text that we explained. You go to the file and download as .jl as a Julia file, and that way you will just get the Julia code, not the other text.
Yeah, and there is also I'll post in the link. There is now a Jupyter desktop app, which many people like, and actually works looks the same way as
a Jupyter notebook.
There is a Jupyter.
Okay, yeah. So let's not add more complexity, I think.
Yes. There's so many options to open Jupyter notebooks, but you can use whatever you want. I'll just put it in the chat for people who are interested. So maybe again, Bobo, you can start discussing the notebook.
Yeah. So I'm going ahead. Yeah, please follow with me. And if you have any questions, because now I'll talk about how the ML algorithm are dealing with the data, so that we are generating ourselves. This is synthetic data, but it is well understandable. But if you have any question, please don't hesitate to ask. So now, as we have downloaded all the modules that we need to execute our the clustering tools and to visualize the results. Now we are going to create a data set. So at first we are creating a vector. There is A, B, C. So we are creating random data, that is, and finally we are creating a matrix. So A, B, C, this is how, if you write it, you will get the matrix. So I am running the code, you see the star, and it's done. So it created a data matrix, which is 15 by 3, because each A, B, C, each of them has are vectors, and by 15 by 1. And when we concatenate them, then we get 15 by 3 matrix. So this is a 3 signatures. It means so, and each of the signatures has 15 rows. It means we have 15 data points. And so 3 types of data, and each type of data has 15 values. Let's explain that way. And now we would like to see how the data plot looks like. So we're using maths as a plotting tools, and it uses Cairo. And Julia has like every first plot in the Julia repo or notebook. It takes a while, but after very first plot, it will be smooth. And that's why it's taking a while, but you'll see later that it will not show any issue. Okay, so Erin, this is clustering. This is, if you go to unsupervised underscore ML, and then you'll get clustering underscore blinds underscore sources underscore separation. So this is the data looks like. Okay, so let me explain again. This data set has, think about 3 attributes, and 3 attributes has like 15 values, but 3 attributes or 3 variables. And this is just, we are defining the same thing, this ABC, this matrix, as a W. So let's define this as a matrix, and now this data says as name, which is W. Now, so you can think this W as water, this in 3 different buckets. Okay, we have water in 3 different buckets, and they are all different. Okay, now you pour them in a single bucket. Now all the waters are mixed, and then we are collecting data from that single bucket from 5 different locations. Okay, and all of them would be different, because in subsurface the mixing doesn't happen homogeneously. It's always heterogeneous, because the reaction is heterogeneous, the underlying system is heterogeneous. So we get a different value at different locations. So, and this is what this H matrix, this is what it tells us. So we have defined, okay, let's suppose we have 5 sensors or 5 oils. that we are getting data from. And so you see the 3x5 matrix. So it's 5 sensors or 5 locations, and we got 3 signals on this H matrix. So this is a different matrix. Okay, this is so W was actual data, and we put them in one bucket, and we're getting data at 5 different locations. And that data is represented by H. So that's what we call it attribute matrix. And on the very first column, you see that 1, 0, and 3. So it means that the first one, it dictates signal 1, and the second is 0. It means this signal is not impacted by or affected by signal 2, but the third value 3, it means it is impacted by the third signal. And the second, the 10, 1, 0, this signal is saying that this is highly impacted by the first signal and little bit impacted by second signal, and it is not impacted by at all by third signal. Similarly, this third column, what is saying, it is impacted by only second signal. And the fourth column is saying it is heavily impacted by second signal or this column, the B column of the W matrix. And the fifth column is saying it's mixed up, like it's getting impacted from all over the like A, B, C signatures of the W matrix, but mostly impacted by signature 3, signature 2, and slightly by signature 1. Okay, so this is all we are defining it. Okay, and now we are creating a data matrix. So it is now W times H, and so this is what we'll get. So this is the data matrix in real life. So we get 5 by 15 or 15 by 5 actually. We have transposed the matrix, and this is the data matrix looks like. Monty, are you there?
Yes.
So do you want to add anything about the W and H matrix?
No.
Okay. So now we have data at 5 locations. And let's plot them. So this looks like now the real data, and you see that now the plotting function is working smooth and is fine and fast. So now we apply clustering. So we in the top cell we imported clustering, and there are several kinds of clustering: k-means, dev-scan, hierarchical clustering, but we are here showing only k-means. So you have to find out what is the best tools for your problem. But k-means is a heavily used clustering tools because it's simple and scalable. So now if you run it, it will it's not already done. So it will give you the clustering, the number of clustering. So we ran for 3 clusters. So we feed up the data matrix H, and the 3, that's the number of clusters we would like to run. We would like to run for 3 clusters. So we have to manually set it up whether we would like to run for 2 clusters, or 3, or 4, or 5. And it will give us the center of the cluster. Okay. So it will give us the center of the cluster. So this is the matrix, the M, the center matrix. And And it will also give us the size of the cluster, like how many. Okay, so now we got 3 clusters because we defined three clusters, and each of them has like different number of size. Size means one cluster got 6 data. So, and the next one gets 6, and the third one gets 3. And this is based on the center of clusters. This 5 times 3, 15. So out of this 15, it's getting 6, 6, and 3. And we also get what data points are assigned to them and how many numbers. So we get that too. And we can also plot them. So I'm plotting them. It's running. And this has created this plot, like how are these data clustered. Okay, one data, this purple, is on the left side, and the second cluster is in the middle, and the third one is at the right end. So it means on this 15 data points, we got these 3 clusters. So clustering is a classification tools. It will basically separate the data point based on their values and their contribution. So K-means clustering tries to find the best center. So for these 3 we define, okay, do clustering for 3 clusters. So at first it starts with random clustering. It means it starts with 3 centers, random centers, and then it tries to optimize the best value, like which centers, like these 3 centers best demarcates themselves better, and that's how they get their best demarcated boundaries. So, and this is their boundary, like they are all equally distributed now. But the problem is, like, we have to define, we don't know whether if 3 is the best signal or not, or 3 is the best cluster or not. So we have to find what number of cluster is optimal or best for the given data set. And that's why we have to run this clustering for multiple clustering number. Like we'll start from 2 and to the number of dimension of the data. So here we have data like we have 15 attributes and 5 locations. So it means we can get up to 5 clusters here. Okay, so now there are multiple metrics to find out the appropriateness of the clustering. Suppose the elbow, cost tabulation, RAND index, variation of information, P measure, and mutual information. And also there one more tool that's called silhouette width. So silhouette width is the most used metric, but however, the metric is also data independent. So what I suggest whenever you apply this kind of tools, I think we have to investigate all this measure and plot them and see which one is best, finding the best clustering. So here for the demonstration purpose, we have shown the silhouette width. So silhouette width is mathematically it's just a cosine norm, the equation you see here. So that's the equation. So for the silhouette width, we need to find the distances. So distances among the data matrix X. So here we imported a distance on this cell, it's running, and calculating the distance matrix. So this is now we got the 15 by 15 matrix, and the diagonal all values should be 0 because they are calculating distance for the same location. That's why they are 0. And the off diagonal, the upper triangle or the lower triangle should be the same. So now calculate the silhouette width. So, okay. So this is the silhouette width for cluster 3 because we defined only for one cluster is 0.58. So now we are running for the clustering for 6 different clusters. So I start with 2 and then it goes from 3, 4, 5, 6, 7. And so we are using the above functions like this function for 2, 3, 4, 5, 6, 7 clusters and storing those value in the silhouette width. So in the line 29 cell, the second line silhouette width, we are storing all the silhouette width value here. And you can see that we get all those silhouette width values. So now we can plot them and see which one has the most, the best silhouette width. So here it's important to note the silhouette width, the highest is value, the better the outcome. So this is the plot you can see. For the cluster 5, we get the best number. Best silhouette width. Not so second is the best, but the 5 is second best. Now, here's the thing. So when cluster number is 2, in general, we get highest value because it's easily can demarcate the boundary in the data set. However, it doesn't mean that that's the best results. So there we have to utilize our sense in the data, because what is telling us data? So we got data at 5 different locations. So it means there should be at least like there should be 5 different kind of data. So 5 cluster would best represent the data set. And so here that's why is doing it good, because here, okay, in the explanation I said 4 because I initially used only 4, but actually now the H matrix is the 5, so that's why it's showing the number of cluster 5 is good. So in a nutshell, although the 2 is highest, but 2 is not actually good for representing or explaining the data, because we collected data at 5 points, so 5 should be our optimal cluster, and the silhouette is also saying that. So there are more clustering to anyway. Before going forward, do you have any questions on it? And also, anyone has problem running this script? Okay, so went wrong. Yes, so I think exercise, I created an exercise, and that is based on youth of force, and we have also published a conference paper on it. So I'll let you guys run this code, but first I gave you this line 3, this cell. I have imported this data set. Now on this geo data, you have to run this script. So what this data set is telling us, we have data of 22 attributes, and the attributes, these attributes is borehole temperature, temperature gradient, temperature at 200 meter and 400 kilometer depth. And then we have heat flow, gravity, then INSER, then seismic time. Then we have the groundwater chemistry data that includes pH, sodium, potassium, calcium, magnesium, iron, then silica, boron, lithium, and bicarbonate ions. So we have total 22 types of attributes at 102 locations. Okay, and then we also did some log transformation, because all the data, they are not equally distributed. To bring into the same kind of distribution, some data needed to be in log transformation, and we did this in these 2 lines, actually in these 4 lines. So and then we okay, at first we have to run this, import this data into the machine, and then run the data, run the K-means clustering. So this is your exercise. Please go ahead and do. So at first you have to define the data. So as I said, first 2 columns consist locations. So we have to get rid of those 2 columns, because we don't want to run the locations. We run the value in the locations, because locations often has high values that will artificially impact the algorithm. So we'd like to exclude the locations. We just want the values in those locations, and that's why, and you can do this. So this is the data now. And you guys can try running this algorithm, the clustering algorithm on this data, and run for only 3 clusters or 4 clusters and see if it runs. Yes, went wrong. So, okay, so not 24 dimension space, it's 22 because we are excluding the first 2 dimensions because those are locations. We don't want to include them. So it would be 22 dimension space. Actually, we should have a lunch break. Monty, how long do the lunch break is?
Excuse me?
So we didn't give a lunch break because we're close to 12 here, and you want to give a lunch break?
Sure.
So let's do this exercise together, and probably at 12 at our time and at 11 at Washington time, Pacific time, we can go for lunch for how long, Monty?
I mean, I'm fine. I'm not taking lunch, so for me it's fine anytime. So ask everyone.
Okay, so 15 minutes or 30 minutes, I think is based on.
No, 15 minutes is too short.
Okay, then 30 minutes. Okay, then we'll do a lunch break. Mountain time 12, from 12 to 12:30. So here is pretty important thing to share. At first, I created a data based on the geothermal data. So I selected data on the 22 attributes, excluding the locations. And you can see the data, the distribution is pretty, they're pretty like diverse. Some value is from 14 to 30, some is 1 to something, some is from 6,000 to 7,000. You will get pretty bad results from this. So we have to create normalization. Okay, so you have to transpose the data. Okay, so on this exercise, what I did, at first I imported the data from a file in the data directory, in the tutorial directory, and it's called force geothermal data reconstructed. And then we selected only the 22 columns because we don't want allocations. And this is the data distribution. And then I ran clustering for 4 clusters. You can just change this value and plot it. You'll find the difference. So at first, without any normalizations, normalization means we are keeping the data value between 0 to 1. And so in this cell, we didn't do any normalization. We just did the whole data, and we have to do transpose of the data, which is just the apostrophe s. And you can then it is just transposed, and then I'm just plotting based on the locations, latitude and longitude, and we can see their distribution. So at first we ran for 3, and let's see, 3 looks like this. If we do 4, and this is the 4, and if we do 5, it looks like mixed up. It's not there significant difference. But so what we found for our paper, we found the 4 cluster is good. There are kind of some kind of boundary between the locations. And then we also did normalizations, and normalizations and perform for 4 clusters and create that plot, and it looks like this. So even if you run for 3 clusters, it looks like this. If you run for 5, then it looks like this. So now we can run these steps, like you select the cluster number, it will generate from 2 to 22 because we have 22 attributes. So our cluster number here should be up to 22. You can do also opposite. You can run for 2 to 120 locations. either way, and calculate the silhouette width and plot their silhouette width value and see which one has most like highest silhouette width value. So I think we have time, and I'll also run the silhouette with this scheme and say which one is the best. So at first we have to create a distance matrix. The silhouette width is a cosine norm, or is kind of distance metric. So we need distance, and then okay, we will run for up to 7 or 8 clusters, and then we'll plot them later. Let's run this. And it is pretty fast. Initially, it was showing error because I put the wrong distance matrix and wrong data. So now it works fine. And let's plot it. So it looks like cluster 5 and cluster 7 is good to represent this data set based on the silhouette width. So here it comes to the like judgment and best understanding the data, because that's why I think machine learning needs to be a one science between machine learning and domain expert who knows about the domain good and also knows the good machine learning. He can best explain any machine learning outputs. And I'm giving you this script if you have not run this on this chat box so that you can run and see the results by yourself, because it is not in the notebook there yet. But I'll push it to the GitLab repo and you can download it later. So please let me know if you have any questions about the data more, because on each of the method will use the same data so that you can understand how each tool is doing on explaining a same data set, and which is a real data set that we got from UTHA-FORCE. UTHA-FORCE is a enhanced geothermal system laboratory. Like they drill a lot of oil, they collect a lot of data, including water, geothermal data, seismic data. So we gathered them and processed them, and now we are utilizing that data set for this workshop, and so that you guys can better understand how we better utilize ML tools for real geoscience data. Actually, let's plot with 7 cluster. Okay, 7 cluster looks like this. And 5 looks like this. Okay. Okay, so yeah, let's take a lunch break. So we'll be back at 12:30 Mountain Time, at 12:30 p.m. So see you then.
Thank you.
Thank you. Have fun. Thank you.
I want to add one more thing to Monty and Bobo. Actually, I tried to reinstall the JLD2 and other packages, whatever, in the Jupyter Lab, and seems to running, but still got some error. So I will try to catch up, but it seems to improving.
Yeah, and again, you can run Jupyter in Jupyter Lab. I prefer to run it in VS Code. So there are many different options how to run the Jupyter notebooks. Browser is the most common, but maybe the ugliest.
Well, I think I can run something after I install all this package through Jupyter Labs for some reason, and I do found that there's some similar issues that post in Google, and seems like maybe just the directory issues that maybe when we update Max and they just change the directory. So I will try to figure it out and catch up in the afternoon.
Okay, thank you, and sorry for these issues. And for us, it's very good lessons learned.
Yes,
thank you.
And please let me know if you have any questions.
Hey, actually, even I've been struggling with this JLD2 thing. It's still been going. I've been following the lecture, but I've not been able to follow by coding with you. So, I mean, I think I'll just follow what you're doing and try to fix this later.
Yeah, and by the way, I mean, all these notebooks and scripts, we're modifying them all the time. So we keep updating our software. So if you discover any issues, let us know. But also, everybody can go and follow these notebooks on their own pace. They're not going to disappear. They'll stay there. So you can continue doing this later on, not only within this course.
All right. If the final Jupyter page notebooks can be uploaded later, that would be nice.
Yeah,
yeah.
Yeah, I just pushed new changes based on the typos that I saw here and there. So Git allows you relatively easy to keep updating files. So at the moment, there is a new version there, and Bubu will be updating as well what he's doing right now. So, but yeah, thank you very much for your participation and interest. So talk with you in 30 minutes again.
Yeah.
Cool.
Okay, have fun.
Have fun.
Anong budlega name
Okay, let's start again. Thank you all for coming. I hope you had an excellent lunch. So, yeah, so far we have explained Julia, how to install packages, and hit some glitches. And Larry did some amazing job. He figured out how to work on this. Please let me know if his steps work for you. And then we covered k-means clustering. So k-means clustering is good for like understanding the intrinsic dimension in the data rather than the whole data dimension. Because whole data, like for this use of first data set, what we have shown here, we have 22 attributes and 102 locations. But so 22 dimension is not good to explain the data set. Rather than what we found, this data set can be explained by either the optimal number of signal is like with the 5 or 7. So we can find out the optimal number of cluster and define the data set based on that. So that's one thing. We get the data optimal data dimension in the data set is k-means clustering. And also for supervised learning, for supervised machine learning, we need some labeling, but without labeling, supervised learning is not good. And we do that using like, we manually do that. And we can also use k-means clustering doing this, just that thing, like labeling. So that's one of the beauty of unsupervised learning. It can help you label the data set. And then we can use that label data set for supervised learning. So, and also one more thing, k-means clustering is classification. It's not regression. It gives us the what cluster is where it's located. So it's kind of classification task. It's not regression. So now we'll go to the next common used machine learning tools, which is principal component analysis. Again, on the same data set of what we used in the clustering, and then we did a simple exercise on use of force data set so that you can get better understanding how and what tools is doing what. So principal component analysis, or PCA, is an orthogonal projection to convert a given set of observations to linearly uncorrelated variables. So what it does, it finds the center or mean of a data set. Like at first it creates, based on what we define, the number of principal components we would like to get from a data set is 2, 3, 4, 5. And based on that, it calculates the mean or the center on that dimension, and then it creates an orthogonal line from data to that center line. So that's what it means in a brief, the orthogonal projection. And it's really good for reducing the data dimension. So whatever data dimension you have, it reduces, and that helps to better explain the data set. And also it portrays the interrelationship between variables and display them in the form of PCA, like in what direction most variance happens and what direction we don't have any variances in that sense. And that's actually principal components. Like the first component has most variance, the second one has less variance than the first component. So gradually it decreases. And it is really good for observe trends, jumps, clusters, and outliers. But it has also some disadvantages, like good for continuous variables, not relevant for categorical unless you manually do it. You can do it, but it is not intrinsic feature of PCA. And then PCA approximates the component variables, which is like, it simplifies the problem of dimensionality. And that sometimes causes the accuracy. So we sometimes loses the accuracy. So
we should be careful, like, okay, we are reducing the data dimension, but are we getting the accurate results or not? So those are pros and cons of PCA, and in a nutshell what it is. So again, we'll do this, we'll just run the cell, and it's running, and okay. Okay, so whenever you see the number instead of a star, it means it's done. So that's what is done. And now we are creating again the same three signatures or three types of data on 15 attributes. So 15 is attributes and 3 is types of data, types of signatures, or types of water, what we say. And we can plot them here. So we are running again. So it's a different notebook. So it will take some time for the plotting the first plot, but later on it becomes very fast. So it's running. Yeah, so just I plotted, and this is what looks like the data matrix. And let's create. So I plotted just the vectors. Now we created a data matrix W and the same like before, and also the age matrix. That's the attribute matrix at 5 different locations or 5 different sensors. And now we are creating the data matrix, which is multiplication of the actual signatures or types of water times the sensors or locations. So this is the data matrix 15 by 5. So our goal is to find how PCA reduces this dimension. So the actual data distribution looks like this. Now, PCA is a multivariate statistical tools, and that's why it's in the multivariate stats package. We already installed that, and also we imported this on this session. So on multivariate stats, you see the .pca. So it means we are now fitting this data using PCA, and maximum output dimension is 4. So now you can see, okay. So it's done, it's pretty fast. So we're fitting, it's giving us some the principal ratio, output dimension. So principal ratio is here kind of accuracy matrix. If it's 1, it means it did a good job. And also it provides, okay, what's the input dimension, what's the output dimension. So you see the outputs are here, age matrix, which is 3 by 5. So 3 is the main dimension here. So that's why, although we put maximum output dimension 4, but eventually it didn't go that far. It stopped at output dimension 3. And then we can reconstruct the H matrices using. So now we have the coefficient matrix or the variance matrix of the PCA, and we can utilize to get the H, which is WTA. And also we can again reconstruct the actual data matrix. So here X is the actual data and XR is the reconstructed, which means we get some coefficient matrix, one coefficient matrix, placed on the PCA now like this. And using that, and also the reconstructed H matrix is not it's reconstructed H, and we can utilize to reconstruct this the actual data matrix X. So this is XR, and let's find out their root mean square error. So root mean square error is to the negative to the power 15 magnitude, which means it's pretty low. It means it really matches the reconstructed data matrix is really good because error is low. But H and WT they're different because it's not exactly they're not finding H matrix rather than it's finding the variance or the how differ this along the one dimension of the one principal component or second principal component or third principal component. That's why it's large. But if you plot the original data matrix, the X and XR, you'll see that they closely match. So this is the original data matrix, and let's see what you see in the reconstructed data matrix. So if you match, so this is the original data matrix, and this is the reconstructed data matrix, and you can see that they closely match. So what we found here that we can even output, we can define output dimension 5 and see still you get output dimension 3. So it means with 3 principal components for this data set, we can really represent the actual data set with 3 principal components. And we can reconstruct the data set. And then again, using this variance, we can explain the data set. So here, let's create the same data set like what we did before for the clustering. And here, again, we can do without normalization and with normalization. So here I will start with normalization so that it gives us better results. Okay, so this is the normalization technique that's we getting from NMFK tools, NMFK module, and from there we can normalize the data matrix and read this data from 0 to 1 range. So now let's copy the this PCA tools. Okay, so input dimension is 22. It means it's 22 attributes, but we ran for maximum output dimension 5, but at 4 it got really good accuracy. So now let's reconstruct the actual data matrix, and then see the error. So again, here we are also transposing the data matrix, not just actual data matrix, because we are trying to reduce the dimension along attribute space, not the location space. Okay, here, so this is the real data, and we got accuracy around 4.5 negative power 6. So I think this is, for my experience, this error is pretty low, because in real data set, we often don't get that much close match like what we got in the synthetic data. And we can also plot this principal component axis in a 3D domain. Anyway, we have not plotted here, but we can do that. And we can also find that along what dimension, what kind of attribute is dominant or not. So yeah, on this data, on this 22 dimension, we have 22 attributes on the first data, but the only 4 dimension is quite good to explain the data set. Okay, if no one has any questions, then I'll jump onto the another unsupervised tools, that's NMF, non-negative matrix factorization. Monty, are you there?
Yes.
Do you have any special things for PCA, like classification or regression, how to best utilize them?
No, I mean, I'm fine.
Okay. So another unsupervised machine learning tool, which is non-negative matrix factorization. And we can utilize this tool as for both classification and regression. What it means, we can classify the data set, also we can predict the data set. So what it means by predict, like people in general understand that unsupervised machine learning, it just find the correlation between variables or attributes and find their importance in the data set, but they are not good for prediction. Actually, that is wrong. So with this NMFK to NMF or NMFK, whatever the unsupervised machine learning tools, we can do both. We can find the importance of attribute in a data set, and also we can use, because we find the coefficient matrix and utilize that coefficient matrix for predict. Like suppose you can split the data set into training and testing. On training set, you train the use this data and get the coefficient matrix and use that coefficient matrix on the testing data and predict the outcome. So we can use this tool for both classification as well as regression or prediction. The main advantages is it reduces data dimension. Like on PCA, we have created a data matrix using W and H. So, but it couldn't reconstruct W and H. It only reconstructed the data matrix. But NF can reconstruct W, H, and the data matrix. So that is a really cool feature of NMF. And it automatically identifies sparse or interpretable signatures, good for outlier detection, can be used for any data set whose elements are non-negative. So here's one more thing here, because many machine learning tools are not interpretable. That because they are not additive. Additive means when you analyze data for both negative and positive values, then you don't know what is going on, whether it's just adding or it's also subtracting. So in that case, we lose the interpretability. But NMF is really good because it only takes non-negative values. So when you feed the data, somehow you have to manipulate the data negative to positive if you have negative values. And then whatever signal you get, whatever data metrics we get, you can interpret that because it only adds, it doesn't subtract. And it has very diverse application till now. For example, it can be used for documental clustering, because then making recommendations like in Netflix or in any consumer products selling. Then visual pattern recognition, such as face recognition, the gene expression analysis, feature extraction, then source separation, etc. It has diverse uses. So it also has disadvantages, like elements in the data matrix have to be non-negative. That's the main feature. That's why it's interpretable. So we have to be careful how we make the negative value to positive value, because that is very important when we interpret the data. And it is hard to converse. It converges for a small data set, but when it is in a dimension in a million scale, then it takes a lot of time. And also not so much scalable, like for large data set, we cannot scale it quite good yet, but people are working on it. Hopefully we'll get a scalable algorithm soon. Then number of optimal signatures is hard to compute. It's like K-means clustering. We don't know what cluster is optimal. We have to use another matrix like solutive width to find the best optimal solution. And initial assignment of weights, like what it does, suppose you have data matrix, it is split into W and H. So it initializes with the random values. So if the actual value and the random values are close, then they converge pretty fast. If not, then it takes a while. And it's a random algorithm. So whenever you use it, you don't get exact results every time. You get overall results would be similar, but not same. So those are the main thing about non-negative matrix factorization. And I'm explaining it more than the other two methods because it's to your science audience, it is pretty new tools. And if you have any questions, please let me know about this method, this tool. Now, yeah, I'll run this code again, the same process. So here we are not using multivariate stats or other few tools because we only need here NMF, and we're using NMFK to plot until normalized matrix, and mass is for signature like plotting, and random is for random generating the random values. So it's all still in the star sign. This is done. Let's go to the next. So again, we are doing the same analysis so that you can better understand how the data is generated and how all the methods are doing their work. And let's plot it. So again, as I said, this is a different notebook. So it's a different new session, completely new session. So it will take some time to plot the very first plot, but we get there. Okay, so yeah, so it plotted. So this is the data set looks like. And let's create W matrix and then H matrix and then create the data set. So now the data set has 15 rows and 5 columns. So what it means, 15 attributes and 5 locations, so 5 sensors. And here we are now we apply NMF, which is analyze data matrix, and it will identify the number of unknown mixed signals in data matrix. Basically, it will find 2 matrices. So X is a big matrix, and it will reduces the dimension of matrix and create 2 matrices. That's W and H. So now here we are doing, so NMF has pretty high level function to low level function. It means you don't have to know PT details, you can run it. And if you want more control, then you can go to low level function. So it's running, and as you can see, PC and clustering was fast, but here it takes a little time, but still converges. And the objective function here is, so this converges after 571 iterations, and it converged successfully. That's why it's true. And the objective function value is 0.02. What it means is, so we have actual data matrix X, and we reconstructed W and H, new W and H, and we multiplied them and we reconstructed the data matrix. And the objective function is the difference of those values, L to norm of those 2 values, and that value is 0.02. So that's what it tells. And so we can define what kind of objective function we would like to use. It has many functions. We can utilize them based on our target. And we said, okay, maximum iteration is 1000. And whenever it goes to the tolerance limit, then it converges before the maximum number of iteration. Now let's look at the reconstructed W and H. So NMF results, it gives all these values, the number of iteration, convergence, whether it's true or false, and objective function, and also the reconstructed W and H matrices. So let's see, is their value, and H is the reconstructed. Like is HE is the equivalent of H. And we can plot this is the original signal, okay? So the top one is the original signals, and the bottom one is the reconstructed signal. And yeah, of course, there is some discrepancy, but you'll get the overall trend. And same thing here. So this is the original mixing matrix or attribute matrix, and it's still plotting. Let's let it plot. Okay, this is the original matrix, and this is the reconstructed matrix. So it means we can recreate this original data and find their optimal signatures. So here, and also you can find, okay, what would be the root mean square? So we can calculate that. And whenever we explain the data set, we can say, okay, this is the accuracy range. So we can explain data set in both way. But this is the trend, we got the trend match, and the accuracy is whatever value we get. And also we can find, so this is the, because in original data set, we don't get that. Here we are getting it, but in original data set, we don't get it. So this is the reconstructed matrix, and based on this plot, we can say, okay, for the signature one, along this direction, okay. So the second variable, second attribute is important. On second signature, fourth variable and fifth variable is important. On third signatures, first and fifth variables are important. So we can create the data set, as well as we can explain what attributes are affecting those, like the data set most. So we can do both. So that's the beauty of this tool, that we often don't get in the supervised machine learning realm. So I'll let you explore by yourself at your leisure time, because this is the same thing like what you did in the PCA and the clustering. You just bring the data, normalize it, and apply this tool, and you can reconstruct the data matrix. But of course, this objective function would be more than this value. Yeah, if you have any question, let me know, because we have a lot more things to cover. Okay, so yeah, there is no question. So I'll move forward with NMFK. NMF and NMFK, they're kind of similar, but NMF has one thing that it's hard to think. What is the optimal solution? Like, at what dimension the data matrix would be split up? Suppose in our data set we have 15 by 5. So this is the data matrix. It's 15 by 5. So what would be the dimension of W? What would be the dimension of H? And we have to do that is by manually. And that's kind of bottleneck. Here we solve that problem using a specified number of K. So K is, it comes from K-means clustering, and Monty, our course leader, he and his group, and we are writing, we have built up this tool to solve that issue, how we can split up and we can track their convergence, their accuracy, those things. And also it has been selected for R&D 100 award for the finalist. I hope we'll get the award. So this is built in Los Alamos in our group. So the NMFK is the same thing. It reduces data dimension, automatically identifies sparse and interpretable signatures, good for outlier detection, and could be used for any data set whose elements are non-negative, and same application as NMF. But the number of optimal factors or signatures is easy to compute based on the loss function and the cosine norm. Here, the cosine norm, as we discussed in the clustering, the silhouette width, that is the cosine norm mathematically. So what we do, we split up for, suppose at the first we start with 2 signatures. So we get, and we done for suppose 1000 iterations. So we get 1008 matrices. On that 1008 matrices, we run k-means clustering and find their cosine norm or the silhouette width. So like this, we get the silhouette width for 2 cluster, 3 cluster, 4 cluster, up to the maximum data dimension that we are seeking result, and find the most or highest silhouette value, and also the reconstruction error, that NMF, what I discussed there, the reconstruction error, like the original matrix, the X, and the reconstructed matrix, which is the multiplication of W and H. So based on these 2 matrices, like the reconstruction error and the silhouette width, we find the optimal signal. So on NMF, we have just 1 matrix, that's the reconstruction error. Here we have 2 matrices, the reconstruction error and the silhouette width. And silhouette width, what it does is find the best correlation among the attributes. Suppose here we have 15 attributes, so it will find the best relation between those 15 attributes, and it will provide us a good understanding the interrelationship between or amongst attributes. And it has same limitation as NMF. So already let's run this. Already we have all the module that we need. Let's create the data set. Here we have to import. So yeah, it's the very first plot, so that's why it's taking a little longer time, but the next plot will be pretty fast. Okay, so this is the series plot of the W, and this is the attribute matrix H. So we are defining here what would be the actual data. So this is the actual data as before, and see how they look like. So we have 5 sensors or 5 locations and 15 attributes. So now here we have different X. So again, here we are not normalizing the data because the data distribution is quite close to the range. If the varies a lot, then we have to normalize the data, and NMFK has that built-in function, normalize by column or normalize by row, we can normalize. But here, as the distribution is close, it's almost Gaussian, so we are not normalizing and still getting good results. But in real data, we have to explore that too. How is the distribution? Okay, so now we're running the NMFK execute. So it means it will execute NMFK, and we'll get W and H matrices reconstructed, not the original, and their fit equality, which is means like the reconstruction error, the robustness, which is the silhouette width, AIC, there's another metric, and the K-opt, so number of optimal signal or number of optimal cluster. And here H is data matrix, and 2 to 5. So there we are defining, okay, you run from 2 number cluster to 5. We can define more, okay? And we're not saving anywhere, we can save here. If it's true, and if we show the result directory, it will dump all the files there. And we can then, later on, we can upload those and analyze further. So let's run it. It's running. And so far I have discussed, including these 4, clustering, PCA, NMF, and this is NMFK. And NMFK will definitely take longer time because it does the same time 2 things, NMF and k-means clustering. But it's exchange of this computation time, we get better. For the complex data set, we get better insights about the data set. But for this kind of simple data set, we get similar results. Okay, so we got it. And here, if you see this, it shows us what is their fitness. It means their reconstruction error. For 2, reconstruction is 13. For 3 is 2.1 to the power -6 power, and then 4 is something, and it's 5. So as so for 4 signature, it has low reconstruction error, and similarity width is not that big. But for 3 signatures, it has reasonably low reconstruction error and high similarity width. So we have to look into these, and we can plot these and see how they are varying, and we also can define, okay, this is the optimal signatures. And let's see how this original signatures, like original signature W, looks like this, and this is the reconstructed W. So overall, they are showing us, they're getting the trend, and then we can also find the root mean square error and find the error. And let's see how is their mixing matrix or attribute matrix, which is H. So this is so in the top one, that's the original mixing matrix, and the bottom one is the reconstructed mixing matrix. So, and the same way you can explain this as we just discussed in the NMF. So in reality, we don't know what would be the attribute mixing, but we can reconstruct this, and based on that, we can explain the data set. Okay, this variable has this much impact on the original data. So yeah, this is an inertial NMF, okay? And later on, we'll show their real-time data, real data on Great Basin. Also, we have 2 examples here. One is on Great Basin, and another one is on the subset of Great Basin, which is in Utah. So all the geothermal data set. And also only one, the Great Basin one, and you can play with the Utah one at your own time, and let me know if you have any questions on that, or email me. Okay, so Monty, do you want to add on NMFK? Anything?
No.
Okay.
Only if there are questions, it can.
Sorry.
Are there questions?
here I'll also request you or recommend you like use the first data that we used in the PC and consider it and run this analysis and see if you can find any important insight about data. Okay, so here in the notebooks on unsupervised ML, here we have geothermal cloud because we are creating another module that is specifically designed for analyzing geothermal data. That's why we named geothermal cloud and then underscore Utah data set. You can run from here for the Utah data set, and it's there. You can see the results. We have some advanced data analytics tool. We have some advanced plotting tools there, and you can get a good predictions from there. But I'm not showing us Utah dataset. I'm showing the different directory. If you go to the SmartTensors tutorials.jl and then go to notebooks and then the geothermal cloud and the Great Basin. So on that folder, Great Basin folder, we have notebook, and the notebook is Great Basin notebook. If you can't run this notebook, please run this greatbasin.jl. That's the code. You can copy and paste to the Julia repo and run it. If you use Mac, use terminal extensions for see the figures, and for other system use Sixel. So here one thing is important, like here for the mapping plot, you see the cool figures. We have to install GMT, which is generic mapping tools. Anyone does work on geodesy or seismic, I think they are familiar with these tools. This is a standalone tools. You have to install on Mac. Windows is kind of shaky. It doesn't work that good. I tried myself. But Mac, it is a pretty stable version. On Linux also. For Mac and Linux, GMT is stable. So you have to install that on Linux and Mac separately, because you can use that without Julia. And Julia has a wrapper that invokes the original GMT and utilizes the Julia facility, like the coding and other plotting tools, all those cool machine learning tools. So you can plot those results using GMT here. So if you don't have GMT, probably you'll not get this plot. So I don't know whether you can follow me or not, but please just stay with me on this notebook. And if you have any question, please let me know. So here we got data in the Great Basin, and it's all data in geochemistry and geothermal data, because we know that the western part of the US, especially this portion of the map, the Great Basin, we have huge amount of geothermal resources. And we are all the leader in the geothermal resource usage, but we are not extracting in our full extent. And that's because all those geothermal resources are hidden, especially we don't know where to drill well and extract the hot water and utilize for power production or spa or domestic heating. People use this, the common using tool is PFA, play fairway analysis, but that uses data separately, find their importance, and they multiply all together and get some probability. So they don't analyze data simultaneously. But NMFK does that, and NMFK does analyze all the data simultaneously, find the mapping function between all the attributes like H matrix and also the W matrix. So here in this data set, our W matrix is the location matrix. Like we have already a huge X matrix. X matrix is, we have about more than 40,000 data points, okay, and 18 attributes. So 18 attributes are like groundwater temperature, then heat flow, and then two geothermometers, and about 14 or 15 of groundwater data, like their major anions and cations and their oxygen isotopes. So let's head first and let's run this code. And so that's the X matrix, and the W. So it will split up into two matrices, W and H. So this is the real data. We don't have our synthetic W and H. So we'll get that utilizing the large data matrix. So here it will splits up two matrices, W and H. W is location matrix, and H is the attribute matrix. So W will tell us about what locations, what kind of resources are there, whether it's a low temperature, high temperature, or medium temperature data. And the H matrix, on the other hand, it will show, okay, for low temperature geothermal resource, what parameters are important or critical? For medium temperature, what kind of parameters are critical? For high temperature, what kind of parameters are important? What kind of parameters we should look for if we go for real our next data acquisition? Okay, so it ran and it ran good. So now here, the CD, if you run by yourself, you have to change this line because it's for my machine. And basically it's going to the Great Basin directory where we have all the data, results, all the things. So it's not in the current directory now. Now I have moved to the directory where all the data we have. And then let's get the data. So now we have the data. We also have headers, like what kind of parameters we are using, can know from here, and the data. So let's get another cell, and so there is one important thing in the NMFK, that no other tools so far, you can do it manually, but no other tools have this capability. You see, there's a lot of blank. There is no data, like double apostrophe S. So it means those data are missing. We don't have the data. But this NMFK still can work on this missing data. It can interpolate and extrapolate. So basically, it uses transfer learning. Suppose here we have good data. For this attribute, we have good data. So NMFK does learns this mapping function between these data points, and whatever it learns, it applies to compute the data, missing data. So there is another beauty of NMFK. It can handle the unknown data, missing data. Okay. So we are now defining how we plot it. Attributes long. It depends how we would like to plot them. And then we are defining, okay, the first two columns, they are X coordinates and Y coordinates. So we are getting those here, X coordinate and Y coordinate. And then we are plotting them here. So I'm plotting in real time. And this is, again, it's a fast plot, so it may take a while. So anyone who is working on mapping probably all know ArcGIS. We also use ArcGIS, but again, it's proprietary and it's expensive. That's why we are trying to let's utilize it, and we are trying to include this GMT that has all the capability of ArcGIS, and we can use this here and see. So as you see, we can plot it here, and this is the plot. Just to plot it now. Now, all the data set and the real-time data set, their distribution is horrible all time. So suppose here temperature is like this on the left, and of course it's like, it's quite good. It's Gaussian distribution, and here is good. This is also good. And this is, again, it's just, it looks like TDS, a total dissolved solid is like univariate distribution with a little bit along all the way around. And again, here is aluminum is just univariate, uniform distribution. The boron is also uniform distribution, looks like. So on this data set, if you use like this, we will not get good results because machine learning doesn't know like how's the distribution. It will find, okay, that data is like uniform, that is Gaussian, and that other attributes all over the place. That's why we need to pre-process it before feeding those data into machine learning. And oxygen isotopes has negative values. So we least value is -18. So we make that positive, and still it works good. And so we have a function called NMFK and data analytics. What it does, it will plot the histogram, and eventually it will show you what is the minimum value of each attribute, what is the maximum, what is the standard deviation, and also show you how many non-NaN there. It means how many real values there and how many missing values there. So let's run this. It's running. So it might take a little while, but here you can see this minimum, mean, maximum, missing values. So we have 18 attributes, and these are the names of the attributes. And you can see like the Great Basin is a great resources for geothermal resources, but yet like people are gathering data, but yet not all the variables are there. For example, groundwater temperature has good data, but aluminum is really like it's 90% missing. And oxygen isotopes is 89 or 90% missing. And that's the real scenario. Like whenever we analyze data, there's a real scenario. Like it will be all over the place, the distribution, and there'll be you'll not get all the data. You have some missing data, and you have to deal with that. So you can see it's plotting. It's already plotted. You get all the histograms for all the attributes. Also get the basic statistics. Now based on this analysis, you can say, okay, some data needs to do log transformation. You can say, okay, log transformation for oxygen is true. Then this NMK will do that, and automatically. Just you have to define, okay, that attributes we need to do log transformation, and NMK will do that for you. And also we have included another thing. It's called inverse distance interpolation to see the data distribution, how they look in the continuous way. Like originally, the data looks like this, like in the place, like in a certain discrete locations. And we have also functions, and that can do the continuous distribution. And we can see their distribution using linear inverse distance interpolation, or you can use kriging anyway. So that's for just say the data visualization. So we have these cool data visualization tools too. And here we found that quartz, calcedony, temperature, and all those groundwater components their distribution is either uniform or all over the place. So we found, okay, if we do log transformation on those, then the histogram would look better, the distribution of the data will look better. So what we did, we created a log v and vectors. So it's basically saying, okay, for that attribute is true, for other attribute is false. We are defining true and false. It's a binary Boolean system. And based on that, it will do log transformation. And let's run this. Oh, I have not defined this. Okay, now you can see it just creating. The temperature is now good. Force is also good. Like we are making those distributions relatively better than what is before. And all we can do with this NMFK is data analytics. So, and it doesn't take long. It doesn't matter how long or how big your data, it takes long. It takes really short time. And based on that, okay, now we know what variable we need to do log transformation using data analytics tool. Now we'll normalize that data matrix based on this log transformation. It means at first we'll do log transformation and then we'll bring those data into 0 to 1 range. And let's do it. And you can find this now log transform data and the minimum data, maximum data, and any other flag you would like to get. So this tree is important because if you want to, so this now you're doing normalizing. If you want to do inverse normalize or denormalize, you need this x min and x max with maximum value and the minimum value. And then you can do inverse of normalization. And then we define the number of Ks. So how many K we would like to analyze? So our data dimension is 8. We have 18 attributes. And we are different. Okay, now we don't want to go that far. We'll run only for 2 to 10. And define the results directory. So all the results would be dumped into results. And define the number of iterations. So number of runs, we are defining 640. And then we can run this execute that as I showed before. And we can give the result directory, case file name, and the data. This is now the log normalized data, and the NK is the number of clusters that we like to execute. Now it would take a long time, probably a day or 24 hours, because this is a huge data set. So we're not running here, but we have the data set in our results directory. And if you load this, we have the load function, so it will not run again. Whatever data we have, we can load it. And you can see the results. So you can see we have for signal 2, 3, 4 to 10, we have corresponding reconstruction error or fitness score, and also the silhouette width. So you see this after 3, the silhouette width is negative. The negative is bad. So, and close to 0 is bad. So we found that signature 2 had 0.8, 0.9 almost, and signature 3 has 0.5. And for the reconstruction error, we have 490 and 315. So for signature 3, reconstruction error is low, and silhouette width is not as 2, but it's still high. So that's why the optimal signature this NMK is defining. Its optimal signature is 3. And we can plot this also. Like, because we define the optimal signature based on these mainly 2 things. Let it plot. So now we see the reconstruction error or fitness. We can see the fitness in the red line, and in the blue line, you can see silhouette width. So you can see 2 is high, and 3 is also high, but after 3 is going downward. So it means after 3 clusters, we cannot explain the data set good. And so based on this data set, we can plot this the W and H matrices and see their distribution. And also you can plot biplots. We have all kind of crazy plotting tools here. Like you can see for 2 signatures, how are they divided. And with this command, the NMFK cluster results, you can get all the figures just from this command, and you will get all the figures that you need to explain the data set. So I'm not analyzing plotting those because already on the folder, so it's there. And you can also see that, so we got 3 signatures, A, B, C. And you can see there, but you can quantify their contribution like numerically. For signature A, you can see those attributes are important along with their contribution. And signature B, you can see their contribution to contributed variables and their contribution. Same thing for C. So now, this is like H matrix here. So this is the attribute matrix. So this is for signature. So 3 signature H matrix. And so here you see the temperature. So red means high temperature, yellow means medium temperature, and green means low temperature. So it means signature B represent high temperature resources, signature C means medium temperature resources, and signature A defines low temperature resources. Now you know what are the high temperature and low temperature and medium temperature resources. Also, for each type of resources, you can also find out what are the main or important or critical attributes. That is one thing. And then you can plot those signatures. Like suppose here, we have say the low temperature, hot temperature, mid temperature. So now you know the exact location of those resource types, like low temperature, hot, and mid temperature resources. So you get the data in both domain, like the attribute domain and the spatial domain. Okay. So using again, those inverse distance of picking tools, you can plot them in the continuous distribution. Basically, this is the same data, okay? And we only take for hot temperature data points, for low temperature data point, and so on. And with those data, we plot those in the continuous map and see their distribution in continuous distribution. So those are their distribution. And also, we can see in the biplots, like how signal B and signal A is correlated, how signal A is correlated to signal C, how signal B is correlated to signal C. And also, the dominant attributes, like what attributes are correlated between those signatures. So this is like classic feature of principal component analysis. So in a nutshell, you can find the location, like, okay, at first we can find the types of resources there. For your problem, it would be different. For here, for geothermal, we'd like to find what kind of resources are there and their spatial distribution and their attribute, like dominant attributes, and also their interrelationship. So you can find all those things. And now, so we know that we have reconstructed W. So if we find W3, so W3 is our optimal signature, and H is our So you'll find those. Now you got the reconstructed W and H, and now you can find out the reconstructed matrix. Yes, data matrix, which is basically the multiplication between two smaller matrices, W and H. And you just multiply them. Now you got the continuous distribution of the data. So go back to our original data matrix. Okay, let's print out here. Okay, so this is the continuous distribution. But if you look at the original distribution, X, you see a lot of NaN value there. Okay, a lot of NaN value there. But here, the reconstructed data, we don't have any NaN value. So using this NaN value, using this reconstructed data, you can use this data set for further analysis, or if you want to do refine analysis on certain part of this basin, you can use this reconstructed data and analyze them. Now, if you may ask, what is their uncertainty? So we can also we can also find that. And that is called, we do that using R2 squared. And for this data set, R2 squared is 0.86. It means there is about 14% uncertainty in the reconstruction. So it means we are certain 86%. So we can also specify the uncertainty in the reconstruction matrix. So this is all about the unsupervised machine learning. We talked about clustering, that is good tools for classification type, and then PCA is good for finding the variance or principal components and reduce the data dimension. And NMF also is good for both classification and regression, and we can reduce the data dimension. NMFK, similar like NMF, but we can define what is the number of cluster we want, and we can plot their value like, okay, let me show you this plot and see, visually see, okay, yeah, here, this is the why this is the optimal signal. Like here 3, this is reconstruction or fitting error is low and selectivity width is relatively high. And here using this, okay, so now we have 3 signal, we can label this as, okay, for that location, the resource is low. For another location, the resource is medium. For another location, resource is high. So we can use this for labeling also, for if you would like to use in a supervised learning. Without manually doing, you can do it using these tools. And also, if you don't want to use supervised at all, you get the coefficient matrix. So if you have W matrix, then put the W matrix and take the H matrix from here and multiply them, then you get the prediction. And also showed, okay, the real data example. So if you have any questions, please let me know. Then from here, I'll jump to supervised machine learning. I'm going to give 5 minutes break before we start to supervised. Okay, let's take a 5 minute break. Here time is 1:45. I'll be back at 1:50 and we'll jump want to okay, so let's take 5 minutes break. Next, did you install GMT using Glue on Mac? Okay. I think Aaron, I think it's, yeah, it's not getting connected to the actual Julia kernel. But are you getting the same problem on Julia repo?
I don't get this problem, but why are you getting this problem? Maybe you have to restart the kernel.
Yeah.
Or maybe you started too many kernels, because maybe if you don't kill properly the kernels, they may stay in the memory. Yeah, now it's working. Now it started. There is a star.
What?
There is a star. I think it worked. The first cell was executed now.
Okay, so let's start with supervised machine learning. So I'd go through basic way. So first we have to create data. Then we have to define loss function. We have to define the network structure. And then train the model, validate and test the model. So those are basic things. So data, define the data, then define loss function, define the network structure. So here today I'll show the multi-layer perceptron, simple multi-layer perceptron or artificial neural network, where every node is connected to each other. So on a machine learning, this kind of machine learning, we basically try to solve this equation. So X is the real data, W is the weights, and B is the bias. So during training, we try to find W and B, weights and biases. So that's the universal equations for linear equations or any kind of multilinear equations. So I'm doing this. We have to use flux. So Julia is flux, and probably Python TensorFlow and Keras we can define their way. So we have to at first run flux, then statistics, and then flux has itself is data loader, and then we can one hot batch, one cold batch. Basically, you'll give them a categorical data, and it will convert them into numerical variables. Like suppose if you give A, B, C, then it will automatically classify them as 1, 2, 3. And then we have to define loss function. Oh, I didn't say loss function. Yeah, loss function is pretty important. For classification, the logit cross entropy, there is one of the best loss functions. There's cross entropy, and you can define your own function. For regression, you can use MSE, mean square error, root mean square error, or define your own function and feed them into their neural networks, and it will work out just fine. And I'll show that when I go to the other notebook. So here I'll use at first using image data. So at first we download the MNIST dataset. MNIST dataset has both training and testing data. And if you put this command and the on this cell line 5 and line 6, it will just automatically split it up into train and like X. Okay, X train is the attributes and Y train is the label, whether it's so suppose this is the number data 1, 2, 3, 4, 5 number data. So this is X train is the matrix data matrix for 1. So if you handwrite it 1, 2 and take a picture of it, then you get a matrix plot or matrix. And the Y train is corresponding label. Okay, it's 1 or 2 or 3. And similarly, X test is the matrix of the numbers 1, 2, 3, the matrix of the pictures, and the Y test is corresponding label. So then we have to flatten it because often this matrix is 3-dimensional because one figure is 2-dimensional, then we have multiple figures or multiple pictures of numbers. So it is tensor or 3-dimensional figure. So we have to flatten it. And then on the X test and Y test, you do one hot batch, and it will automatically classify them as 0 to 9. So basically, in the actual data is like 1, 2, 3, 4, 5 in every 10, or then this function converts them to the numerical value. And then we have the data loader function. What it does, it takes those flattened X train and Y test, X test and Y X train, and define the batch size. What batch size it means. So often supervised learning is huge data set. So we feed them huge data set, but we don't want to train all the data set together. We take part of the data set and train them and update the model. And next we'll take next batch of data set, we train them and update the model. So this is the way. Suppose we have 100 data and we'd like to train only 10 of them each time. So on 100 data, we train 10 first, then the next 10, then the next 10. And this way we train until it reaches to the final 100. So this is what batch size. And shuffle is pretty important. What shuffle means, the way that is there, we don't train them just like that. So we'll shuffle them, the data matrix, and train them. So if we don't shuffle it, what happens? Training gets really good. Training gets really good score, but when you test it with the new data, with the unseen data, then you get bad results. So that's why shuffling is important. And then finally, what this function does, it creates train loader, test loader. It means basically it creates training data and test data. So train data has both the attribute matrix and the corresponding labels or the outputs. So now we create a neural network model, which is this chain. It means you see the dense. So this, it means one layer. This dense means one layer. The next dense is the second layer. So we are creating a model with 2 layers, and the first layer has the product image size. It means the multiplication of 28 times 1, which is 784 times 32. So this is the dimension of the data, and this 32 is their dimension, like number of neurons on a layer. And we also need the activation function. So what it does, so from these two, this product, the input dimension and the neuron, it gives linear interpolation between the input data and those neurons. And then what it does, the ReLU function, it makes it nonlinear. And then those nonlinear values pass to the second layers, to these 32 neurons. And based on that data, it calculates the weights and biases and find this number of classes. So here I said its number of classes 10 because we are using training the 10 images, like 1, 2, 3, 4, 5, 10 types of images, not 10 images. We are using thousands of images, but we're trying to understand the number, numeric value from 0 to 9. So eventually, this neuron, it will spit out whether that image has the pictures of 1 or 2 or 3. So that's the explanation of neural network. And then we define loss function and the accuracy function. So loss function is this log with cross entropy, which is the log trace cross entropy. It means we take log value of there between two, like what we have the actual level and the machine learning levels. So this y hat is the machine learning prediction and y is the true. And there's the log with cross entropy. You can Google it and find their function. So based on that function, they find their loss. That means how many misprediction they're doing. So that's how we do. And also the accuracy function is the sum of difference between accurate prediction and misprediction. So we also define loss and accuracy function here. And then in supervised learning, if you have any slightest idea, probably have heard the term hyperparameter tuning. So what it does, so we don't manipulate data here. Data is true. What we manipulate, the neural network model parameters. That has no relation with actual data. And those are learning rate, it means how fast they're learning. If you put high learning rate, it will try to converse fast, but produce some wrong models. So we have to raise it, we have to tune it. Tune it means we have to test it with multiple values and find out the most optimal value for that. That's in a nutshell hyperparameter tuning. And the batch size is here 256. So we have also find out what batch size we can get a good results on both training and testing. And epochs here, epochs is only 10 because it's a last data set. Epochs means number of iterations they will run. So epochs actually not iteration, just exactly iteration. So machine learning, what does, it runs 1 times. So it predicts once, and then find the calculate the loss function, loss values, and then it back propagates to the input domain. So during this back propagation, it finds the weights and biases value. So that's what the epochs. So it includes two things. One is iteration in forward iteration and the back propagation. So in the forward iteration, it calculates or predict the optimal, like what we're looking for, like 1, 2, 3, 4, 5, 6 here. And if we see, okay, there's, and then see the difference using the loss function. And then we back propagate that to the network and calculate the weights and biases. So that's what epochs is. Here is only 10. That's for the sake of this demonstration. And we have using CUDA. CUDA is like if you have GPU, especially on Windows, then run this on GPU. GPUs has multiple CPUs, but not as sophisticated as real CPU. And it's good for sparse calculation, and artificial neural network or machine learning is mostly sparse calculation. So GPU is good. So if you have GPU, you can parallelize this run manifold. And we can include many more hyperparameters and define this here. This is the smartest way. You can then later on vary this. And then finally, we create a training function. So what it does means, so we created here the data loader, like data feeding function. Then we have created a neural network model. Then we have defined loss function. And then we have defined hyperparameter tuning. So using these 4 functions, so we'll call all these 4 functions or all these training functions. Suppose here the args is the arguments. Those are not critical. Without this, you can run this model still. But with this calling here, we can change these values. And then on the next, from 4 to 11, what we're doing, we are checking the machine whether it's a GPU based or the only just CPU. If it doesn't have GPU, then it will just use CPU. But if the machine has GPU, graphical processing unit, then it will use GPU. That's what this line does. And the line 14, what it does, it just get the data. From the, we download a huge amount of data, but we subdivide into batch sizes and get the data what we need. And then we build a model. So model means we are calling this model. So how the models are, how many layers are there, how many neurons are there. Okay, so based on that, we have to create model parameters. Here is saying model parameters here are not the actual data. It's weights and biases of the neural networks. And PS exactly does that. It finds out the model parameters. It means during this training, it will change only those parameters, only those weights and biases of the neural networks, and update while it runs, while it trains. And here we are training. So we call all the above functions there. And then we are training here. And we are using optimization. So in machine learning, everything is about linear algebra, data, and optimization. These 3 things are important: data, linear algebra, and optimizations. So we have to call optimizers. And this is, we are calling ADAM, adaptive momentum. This is variance of gradient descent, stochastic gradient descent. And it shows pretty good, like people using it a lot, and one of the mostly used optimizer. So using those optimizers, neural network, data loader, and GPU or CPU functions, and the hyperparameter tuning functions, we are training on this, actually this line on 25 to 29, we are training this. So what you're doing, so we got the train loader. So it is splits of data based on the batch size. And then we are reading each of the data size, X and Y. The X is the training data, Y is the training level. And we are transferring this training data to the device. And then we are finding the gradient. So gradient is the, okay, it's a division, like the loss function by weights. That's actually, okay. Loss function divide the model parameters. What it means, we find the loss function after a forward iteration, and then we divide with the optimal weights and biases. So that's actually gradient machine learning model. So every time for each training data, like as I said, I subdivide it based on the batch size. So every time it runs on this small data set, not the whole data set, and it gets new weights and biases, and it updates it every time. For each epoch, it runs for every batch of data and update the model parameters, which are weights and biases of the neural network. And then it calculates the actual accuracy, loss and accuracy. So here, this is the training function, and you can run it, or you have to run. Let's delete this. Okay. Now this function is calling all the functions together. And now we are defining, okay, learning rate is 0.01, and let's train it. So now what it's doing is downloading the data from the module in our computer, and then it's calling all the functions, and it will train based on our defined neural network. Okay, so this starts running, and you see it's training on CPU because Mac doesn't have GPU. My Mac doesn't have CPU, and it's spitting out, okay, for epochs, training loss is 0.717, and training accuracy is 94%, testing accuracy is 94% also. And as you said, return for epochs is 10. So, and you see how fast is the training. Like initially it's 0.17, and the end of the 10 epochs is 0.06, and the training accuracy is 97%, and the testing accuracy is 96%. So now you have the model. Basically, you can store weights and biases and store them and feed the new data, new images. You can get a prediction. But it's hard to predict. The problem is we don't know what parameter, what attributes, not parameter, what attributes or variables in the actual data is contributing to the label. So that's why we call it black box model. So you have to define it now, and also it needs big data. So based on your data, on your requirement, you have to decide, okay, should I go for unsupervised or supervised? So that is the basic building block of a supervised machine learning. I'll recap it again. We have to first create data. Then we have to create neural network model. Then we have to define loss functions and accuracy functions. And if you want to do hyperparameter, we have to define that too. And then call all these 4 building blocks of supervised learning in one place and tie them together, and finally run it on the given data. So yeah, so 4 things: data, building a neural network model, defining loss and accuracy functions, and defining hyperparameter tuning parameters, and then just tie them together and run for training and testing. Now, so that is for whatever you have. Sorry, my phone is ringing. So, but if you would like to more investigate more details, if you would like to find out gradients of each for each model attributes and also the neural network parameters like weights and biases. You have that most easiest control on this Julia platform than any other language. It's not just you define model and train it and test it and validate it. But for our scientific purpose, we also try to dig deeper. And that's what Flux does pretty good job. And that is done by automatic differentiation. That's basically backpropagation. So let's run through simple example, and then I'll see how the automatic differentiation works, how you can more investigate your model. Okay, so this is the function, is 3x squared 2x plus 1. It is a nonlinear function, okay? And if you define, so this is the function, another way of defining function. And if you put f equal 1, it's 6, okay? Because all x equal 1, so they just add the coefficients and you get the 6. Now, we would like to get gradient of this function. So gradient is just, now we are trying to get dx by dy. And you just define this way. So call flux dot gradient. And so just one, it means, okay, so you're defining the function and say df1, and it's calculating the gradient. Okay, so it's 8. So basically, if you differentiate this function, you'll get, and for x, so for x equal 1, then you'll get the 8. And then on top of that, you can calculate the gradients of gradient, which is d squared x by dy squared. And define that function and calculate the gradients. Yeah, that's 6. So that's how you can calculate the gradients. So on the previous example, I showed you just, you don't have to worry about anything what's going on under the hood, yet you can get results. But if you would like to investigate more what's happening under the hood, then you have the option to do that. And you can also define the loss function, manual loss function. So here, so wx is the x is our actual model attributes, which is, this is the function fx equal 3x2 plus 2x, 3x squared plus 2x plus 1. So x is that our model attributes. But for the neural network model function parameters are OS and bias W and V, and we can define the loss function. And let's define for that function, fx function, we define the model attributes x and the neural network parameter weights and biases, and we can find the loss function. So for these random variables, it will vary every time because it's random. You get this 3.32. Okay, so and then we can compute the gradients of the gradients, which is wx plus b. And now, so we have, so how do you calculate the gradients? Actually, this is not important, this line 12 here. So we are calculating gradients here. So we have defined loss function. So I'm telling again, loss function is the forward iteration. We define layers and neurons and propagate through and predict some values and calculate the difference between true values and predicted values by machine learning model. So there's the loss. So we define loss, we get the loss. We define the actual model attributes X. And we also initialize some weights and biases. And based on that, we can calculate the gradient. So let's find out the types, which is basically tuple, and you can access this tuple like this. So this is the output gradients. So one gradient out one is the basically the 5-element vector, and the output 2 is 3x5 matrix, and output 3 is 1. So basically here, here is the data X. Data or output, you have to investigate that. But this is output 2, this is the weights, the W, the neural network model parameters W, and this one is bias. And so without doing the manual, the inbuilt gradient, the defining dense network, you can define model like this and calculate the gradients, and you can easily find out the optimizable parameters, which are weights and biases like this. So it all does automatically, and this is really helpful when you try to investigate further than just getting the model and getting good model and running it. But whenever it hits a hard problem or outside of the range, or even for explain the model how it's moving, you might need it. So yeah, this is what again on this below. This is we have shown dense neural network, then also convolutional neural network, how you define it and tie them together, and how you train. I'm not going on details, but since this is the pretty brief introduction about supervised, please let me know if you have any question about for your problem, what kind of tools you'd like to use based on this discussion. And if you have any question, okay, this is our data, what kind of tools are best suited for your problem, I think we'll try to answer. I don't know whether it is best or worse, but we'll be happy to discuss. Okay, so here another tools I'm building. It is not finished yet. Whenever I finish it, I'll email you guys. So this is on our geothermal dataset of Utah. This is sub like a small dataset of Great Basin. I can show you what portion of the data is there. So this is the Utah map, and these are the data. So we have created used on NMFK to label the data, like basically 1, 2, 3, or low, medium, hot temperature geothermal resources. Now I'm building a model using this artificial neural network to predict with a given data what would be the types of resources. That's my goal. I'm building it. It's not finished yet, but I hope I can finish it soon, and I'll then email you, and you can utilize how to use the real data for supervised learning and Julia platform. Monty, are you there? And I found it went wrong. Found VS Code is useful for running Jupyter. I think that has good connection between kernel and the
Yeah, I always prefer to use VS Code, at least. Yeah.
Okay, I think that's what all I had to discuss about today. So please let me know if you have any questions, especially like in geosciences, because I'm from the geoscience background. And so that's how I think I understand what's the problem of geoscience data and what tools are useful. Monty is also from geoscience background, so his whole life is on this, using both geoscience data and machine learning or any other numerical methods. And what we found, unsupervised is better suited for our data set than supervised. First, supervised learning needs continuous data, but we don't get that mass continuous data. Second, it needs large data, and geoscience often we don't have that kind of large data set. And supervised learning is hard to explain, but unsupervised learning, you can see what parameters are important, what parameters are critical for one types of prediction or not. That's our understanding. That's a fantastic questions. Why not semi-supervised learning? What do you have?
Semi-supervised, and people argue. I have been in a lot of heated arguments. What is the difference between unsupervised, semi-supervised, and supervised? And semi-supervised, in many ways, almost everything is semi-supervised, because fully unsupervised will be when we have artificial intelligence, right? So as long you are putting any kind of constraints, as long the engineers or practitioners or whoever is running the machine learning is putting anything to control how the machine learning works, you can call it semi-supervised. But this is really kind of different ways to call these things. And I'm not that much hardwired. I believe, we need to distinguish the big difference between strongly unsupervised and strongly supervised methods. And everything else, and practically everything, even what we discussed today, is kind of the category in between, but some of them are more close to unsupervised and some are more close to, so yeah, this boundary is a gray area, but I'm not going to argue one way or another. Other questions? Yeah, this is a very good question. I enjoy answering it. Is it hard to convince companies to use unsupervised machine learning approaches? We have been successful. We work with oil and gas companies. We have not been very active with geothermal companies, but this is something that we also kind of something that we're trying to achieve as well. Again, I'll say really very often these days people realize that the purely supervised machine learning or deep learning methods has some issues, and they're not always as applicable as we would like them to be for real world problems, mostly because we don't have enough data to train them, and there are measurement errors and there are many other issues. So I think we don't have big issues to convince people to use unsupervised.
So can you also give, like, I think there's a language problem. Do you have any hints on this? Like how to convince those people? Monty?
Yes, can you say it again? I'm sorry, I got distracted. I got the email.
So yeah, how to convince, suppose the geothermal industry, how do you convince those people like unsupervised is good?
I mean, mostly it's through demonstration. I will say that demonstration and showing the power of the methods is the most practical approach. And
yeah, so think about this, like you get attribute matrix, you get the locations of those wells, also location matrix, and you can show them, hey, this is what you can explain better with unsupervised than supervised. And that would be my take to explain them. Anyways, you have to understand the audience, whether they would like to, they like magic, like the supervised learning, or they like reason. You have to understand that, and you have to try to convince them in that way.
Yeah. Yeah. The other thing which is frequently used these days, everybody's talking about explainable, robust machine learning methods, or machine learning methods which we really understand what's going on. And this is something else that we can also emphasize, that unsupervised machine learning methods are much easier to understand and defend their results because they're not black box.
So can you generate clusters, unsupervised clusters with uncertainty estimates? I said you, so we have to estimate 3 clusters on Great Basin data. Even user force data, if you navigate it, you can see got 3 clusters, and accuracy is about 85% around that. Especially for Great Basin, it's more than 86%. So that's one uncertainty. And we got 3 clusters. So is that what you're looking for, or are you looking for something else?
Yeah. And I mean, as we kind of discussed, I mean, most of the analysis, what we're doing, we're performing this multiple times with random initial guesses, because we don't think that single estimate will give us good result. And all these random initial guesses results can be used to evaluate the uncertainty.
So here's my question then. I was asking the question. This is Shubhajit here. So do you then recommend generating multiple realizations then?
Yes.
Multiple models, basically.
Yes. Yes. And yes. And after that, you can apply then various techniques to rank the performance of different models as well. I mean, if you want to explore different models, I mean, this is also much better than just sticking to one.
And how do you check which model is better than others? Is there any statistical technique, or are we
Yes.
going to use any ground truth?
Yeah, I mean, if you have synthetic problem, then you can use the ground truth comparisons. But if you're solving something that it's real world and you don't know what is the accurate solution, there are various information-based criteria like AIC, BIC, KIC. I mean, they're widely used methods for model selection. And some of those are automatically computed by our codes and can be used. Not all of them, but some of them are computed in our codes.
Thanks. So there is one of the things that I am kind of concerned about, and I started working on this in the last, couple of years, is that many of the attributes, and let's say from the subsurface, when you use, seismic data or even borehole geophysical data, these data are highly interdependent. There's a high interdependence among the attributes in our data. And that's based on your different rock types, then let's say fractures, many other reasons. And we know that in many of the supervised machine learning, they really want the attributes that are supposed to be as independent as possible. So you can maximize information, models are not overfit and all that. And I have looked at data from, from finance and accounting, where they, try to use as independent attributes as possible. And therefore that correlation generally doesn't go more than 70%, generally. I mean, there are square. Now what I'm asking you is this, that we have this inherent nature in our data set, that this interdependence between the data sets, and there are some geologic reasons behind that. How can we, incorporate this understanding into our models, and how can we avoid these things so our models are not really overfit? Because let me give an example here. You will see many publications in geophysics. There is this classic problem of predicting some missing geophysical log, right? And there are many logs already there, and maybe one of the logs, like sonic logs, is missing, and we are using the neural network approach to predict that. Now we know there are some interdependence between many of these logs. So why are and then what happens the moment we are applying that model to a larger area, larger area, then those models results are not consistent anymore because the boundary conditions changed.
Yeah, I mean, so just to answer the first part of the question, correlation between the attributes that are analyzed in supervised machine learning will not cause a problem. I mean, our techniques are specifically designed to account for this situation. So there is nothing to be concerned to put too much variables or something that controls the output, and they're correlated. I mean, the algorithm automatically will identify this correlation. So you don't need to worry to identify attributes in advance which are unique for the problem that you're solving. So these issues doesn't exist in our case. But in general, I agree with you. I mean, there is a lot of problems, even with unsupervised, how we're going to interpret results. And when you have complex data, when you have nonlinear relationships, all these things make the analysis more complicated. And machine learning methods, again, cannot remove the subject matter expertise. I mean, the subject matter expertise is important throughout the analysis. You cannot just think that everything can be done automatically and no human or expert will look at the results. So having understanding of what is expected to be a reasonable result and what might be not is very important. Specifically to the problem to underfitting and overfitting, our techniques also specifically look at this. So all this evaluation of the number of features which are reasonable to be applied to characterize the problem is addressing this issue of overfitting and underfitting. So we also pay a lot of attention on this as well. I hope I answered everything, but keep asking questions.
So I hope I'm not taking time from others. Otherwise, I can continue asking questions.
Yeah, or if you want, you can continue later by email.
Yeah,
or
yeah.
throughout. I
So
mean,
just one last question from me, that in your approach in unsupervised learning, the clustering approach, we have these attributes, and the attributes are common. We have these measurements, and we collect those from outcrops, from the subsurface. We got these attributes. The attributes are not going to change whether we will use supervised or unsupervised approaches. So they will have some sort of relation in some cases. Now, what's your strategy for selecting those attributes? Do you do any correlation between the like linear dependence analysis, and then say, hey, if it is more than 0.8, do not select those, or look at partial correlation, things like those? How do you select those attributes, or a pair of attributes?
We don't select, we throw in everything. We don't remove any, I mean, we don't need to look at those. We can run the analysis, and after the analysis will tell us which are potentially correlated attributes, and they will be binned together. So you don't need to do this in advance. I mean, the algorithm will give you these correlations.
Okay, thanks. Yeah.
Yeah, I think the main thing about this method, you can throw in anything, just see the data distribution of each attribute, like whether they are following whether Gaussian or uniform or those kind of distribution. I think if those are similar, then it will find those correlation easily.
I mean, many of our attributes are highly skewed in nature. Yeah, and that's our distribution if it's not really Gaussian. Just wondering, a very general question. I mean, you guys are doing a lot of unsupervised learning, and I'm working a lot on time series type work. Just wondering that, from your literature review and the work that has been done and the work that you are doing now, what are some of the challenges that we have in machine learning, earth sciences, and what are some of the future research that someone should be doing? Some broad idea. What are some of the challenges that we have now?
I mean, there's several challenges. From one side of view, there is a lot of attempt to theoretically to, I mean, okay, let me just start from the biggest challenge. Even though the machine learning works, there is no mathematical proof that they work. I mean, we know that based on our experience, we have algorithms that work only for some specific neural networks and not for all the type of neural networks. For example, supervised machine learning, there is a proof that this will exist. So mathematically and theoretically, there are many challenges, but from a practical point of view, I believe the major interest, at least for us at the moment, is to work towards bringing as much as possible physics information in the machine learning process, where we add constraints, we add physics models, we add equations in the neural networks so that we can get better results. So at the moment, most of our work in terms of research is to bring physics into the machine learning. So we have something which is called physics-informed machine learning, which is kind of semi-supervised, again, method where we're adding information about the physics that we're solving. And of course, the problem of this is that these techniques are not as general as the one we're discussing, quite classical, unsupervised and supervised, because they can apply to any problem. When you have physics-informed machine learning, it means that they're tailored more to the specific problem that we're solving.
Agree, but then when you talk about physics, we have these defined equations, like so wave propagation through mid rocks and or resistivity, electromagnetics. We have those equations, and we can do that. But then in geology, we have many of our things are basically based on your patterns that you see on the images. How can we use image-based patterns and use that to guide the machine learning results?
Yeah, and the other important problem which is related to this is that in many cases we don't know very well the physics, especially in the geology applications. But still, this does not preclude us, because even if the physics is not perfect, the machine learning will be able to adjust it in a way potentially to address these issues. Other questions? I'm sorry, is my connection lost or everybody's quiet?
No, your connection looks good.
Okay.
Okay, so I think everyone looks quiet. Maybe they're exploring by themselves, because probably they're struggling say, to run this notebook, because everyone seems having issue with kernel issue, like they can run on Julia repo, but not on this Jupyter notebook. So that's why I also download this notebook as a Julia code and copy and paste on the Julia repo and see if it's running correct or not. And also, I think I'm open. If you have any questions, email me, or we can sit down and do 1-on-1 or 2-on-1, whatever meeting, and I'd like to address your concern. Please send the link again. Do you mean this repo, or?
I think about the SmartTensors. I mean, now if
yeah, it's in the.
I'll put the link again.
Yeah, you can do it here. Or also, we send you a PDF file. There's a link there. So if no one has questions, then yeah, I'd like to say thank you all again. And we are sorry that not everyone could follow along with me because of the logistical issue. But if we could do it in person, probably it would not happen. So there's another drawback of virtual session like this kind of technical things. But hopefully we will do it again. We're doing this session in AGU this year in December in New Orleans. If in-person events happen, then we go in person and do this. You're welcome there. And please let me know if you have any questions. I'll try to answer as much as possible.
Yeah, and also any feedbacks you have.
Yeah, any feedbacks are also welcome. Okay, so Cole said Jupyter Lab desktop app work better than browser. Okay. To know. Sorry, Larry. Yeah, please run this on yourself, and we have explained. It's self-explanatory. That's why we made try to explain. But anyway, if you have a question, please don't hesitate to ask me. Any suggested readings for beginners, Monty?
I think only the things that we already have provided. So, I mean, there are plenty of good tools online, but really depends on anybody's preferences. I don't think I can recommend anything else that we already put as the links.
Yeah, so we on every notebook we provided, especially the unsupervised reported mathematical background and also their pros and cons. So, and then for every technique there are 2 or 3 milestone papers that you can read. But again, if you don't have any good mathematical or machine learning background, understanding those papers also hard. I think working on machine learning model is easier than understanding their method, their algorithm. I'll try to go, yeah.
Yeah, I mean, all our papers on our website. So if you...
And our papers are all on website, yeah.
Yeah, so I mean, you can go to our website and you can find our papers.
Yeah, so I think everyone has issue with Jupyter Notebook. And I think in the long term, this is our first time we're offering this course. So we really apologize for this glitchy thing happened, but we'll keep in mind and probably will more go for Jupyter Lab next time. I have not used personally, but I'll try and make sure it was good. And I think Josh, so this recording will be available. John, yes, so he applied. GSA will send out the recording to attendees. So thank you, Cole. Have a good weekend, you too, Stefan.
Yeah, thank you very much, everyone. And again, for us was really very helpful to hear all your questions and comments during the workshop.
Yeah.
Highly appreciate it.
Yeah, all right then. So
hope you have other opportunities to cross paths in the future.
Yeah. Okay, then should we adjourn the session?
Yeah. I mean, yeah. If that's it, yeah. Thank you very much again, and see you soon. Bye.
Bye. And thanks. Thank you for the GSA John and the brother.
Thank you, Bobo. I appreciate that. You and Monty did an awesome job today.
Yeah, yeah, and thank you for arranging this session for us.
Absolutely. Jennifer knows Serena will be in touch. I know you've been working with her, so she'll reach out to you
Yeah,
and
Yep.
follow up with you.
yeah. All right. And thank you, John, for helping us.
Yeah, thank you, Boo. Yeah.
All right, then. Bye.
Right. Thanks, Mitzi. Have a good one.
Thank
You
you,
too.
John.
Bye.
I appreciate it, John.